Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. At midnight by the shore, the ocean seems to breathe. With each silent swell, the water edges forward and then gently retreats, as if following a cosmic lullaby. A broad silver path of moonlight stretches over the waves, shimmering softly. That silvery glow on the sea is sunlight reflected off our moon's face, and the rhythmic tug of the tides is no coincidence. It is the moon's gravity pulling on Earth's oceans, drawing them up and letting them fall. In this tranquil moment, the moon holds Earth in an unseen embrace, one hand shaping the tides, the other painting the night with gentle light. Our moon has always been Earth's steadfast companion, but it was born from chaos. In the violent dawn of the solar system, over 4 billion years ago, a young Earth was struck by a Mars-sized planetary body. This catastrophic impact tore part of Earth's molten mantle into orbit. Out of that glowing debris ring, our moon coalesced. At first, it was a searing ball of rock much closer to Earth than it is today. The newborn moon loomed huge in the sky, and the tides it raised were titanic, racing across the early coastlines. Earth spun faster then. A day was only about 12 hours long, but over eons the moon's gravitational grip on our spinning planet put on the brakes. The tidal tug gradually slowed Earth's rotation and, in response, nudged the moon farther away. Even now, the moon drifts about 3.8 centimeters farther from Earth each year, a subtle widening of the gulf. Yet the bond between Earth and moon remains profound. The moon is tidally locked to Earth, forever turning the same face toward us. When we look up, the features of the man in the moon are the same ones every generation of humans has seen. And the moon's influence goes far beyond the ocean tides. The moon's gravity acts as a stabilizer on Earth's axial tilt, keeping our planet's orientation steady. Without our big moon, Earth's axis would wobble chaotically due to the gravitational nudges of the sun and other planets. Climate might swing wildly. Ice ages and scorching eras could alternate in extreme fashion. Instead, thanks to the moon, Earth's tilt swings only mildly, about 23 to 24 degrees, giving us regular seasons and a long-term climate stability that has allowed life to develop in relative peace. Mars, by contrast, with only tiny moons, wobbles on its axis far more dramatically, a likely reason for severe climate fluctuations on that world. Indeed, Earth is unique among the inner planets in having such a large moon. Mercury and Venus have none at all, and Mars's too are puny. It's intriguing to consider that our moon may be one of the keys to Earth's habitability, a cosmic guardian against chaos. The moon's steady tug has also shaped life on Earth in other ways. In its youth, when the moon rode closer to Earth and tides were immensely high, the rhythmic flooding and draining of coastal areas may have helped spark life's origin. Imagine the primordial shorelines of a young Earth. Water rich in organic molecules washing over sun-baked rocks, then receding over and over. These rapid tidal cycles could have concentrated simple chemicals into more complex ones. Some scientists speculate that the moon's extreme ancient tides acted as a natural distillery and reactor, perhaps aiding the formation of the first nucleic acids, the precursors to DNA, RNA, in warm tidal pools. Whether or not life began there, the moon has continued to nurture Earth's biosphere. The gentle, twice-daily pulse of today's tides creates dynamic intertidal zones, areas alternately submerged and exposed, which are crucibles of evolution. Marine creatures had to adapt to the changing water levels, leading to greater diversity. The rich tide pool ecosystems, teeming with life that must endure both wet and dry conditions, likely owe their existence to the lunar tides. Some biologists have mused that without the moon's tidal influence, Earth's coastal life would be far less abundant and varied. For humanity, the moon has been a source of wonder, inspiration, and guidance since time immemorial. It has marked the passage of months, The word month itself comes from the moon and lit up our nights. Ancient cultures wove myths around the moon, seeing in it gods, goddesses, or spirits. They tracked its phases and held festivals by its schedule. But it was only in the last few centuries that we truly began to understand what the moon is, and that it is not alone. In 1610, when the first primitive telescopes were aimed at Jupiter, observers were astonished to see 4 starry points near the planet that moved from night to night. These turned out to be moons orbiting Jupiter, the first discovery of moons around another world. It was a shattering revelation at the time, proof that not everything circles Earth. Our view of the cosmos suddenly expanded. Earth had its moon, Jupiter had its own moons, and by implication, the universe was not arranged solely for our benefit. Since that breakthrough, we have discovered moons in every corner of the solar system. Even small asteroids can have moons of their own. Astronomers have found asteroid pairs and triplets dancing together in space. It seems nature likes to form moons whenever it can. The general rule is, the more massive the planet, or the stronger the gravity, the more likely it is to gather or form moons. And nothing in our solar system is more massive than Jupiter, king of the planets. So it is fitting that Jupiter presides over a truly majestic retinue of moons. When we voyage outward to Jupiter in our minds, we encounter a miniature solar system of at least 95 moons, and still counting. 4 of them are giant, planet-like moons, the very ones first seen in 1610. These are the Galilean moons, Io, Europa, Ganymede, and Callisto, each a world with its own character. Imagine approaching Jupiter. You would see Io, Europa, Ganymede, and Callisto as bright orbs lined up around the gargantuan planet, dancing in resonance. Jupiter's gravity dominates them, but they also tug on each other in a cosmic rhythm, and their identities have been forged by that interplay. Io, the innermost large moon, is a world of fire and brimstone. It is slightly larger than Earth's moon, but there the similarity ends. Io is the most volcanically active body in the solar system. Its surface is a hellscape pockmarked with hundreds of volcanoes, some erupting lava fountains dozens of kilometers high. When NASA's Voyager 1 spacecraft flew by Io in 1979, it caught sight of an umbrella-shaped plume shooting into space, a volcano actively erupting in real time. Io's surface is painted in sulfurous colors. Sulfur and volcanic gases frost the ground in yellow, white, and orange hues, and black lava fields from recent eruptions dot the landscape. Lakes of molten sulfur glow in volcanic calderas. Gigantic mountains, some taller than Mount Everest, rise from Io's plains, formed by tectonic thrusting from below. Unlike our moon, Io has virtually no impact craters. Any that form are quickly buried in fresh lava or plume fallout. Io is constantly renewing itself. The driving engine of this activity is tidal heating. Io orbits extremely close to Jupiter, closer than our moon orbits Earth, and is locked in a gravitational resonance with Europa and Ganymede. Io circles Jupiter 4 times for every one orbit of Ganymede, and twice for every one of Europa. This resonance means Io's orbit is slightly elliptical, and as it swings closer to and farther from Jupiter, the immense gravity of the planet flexes Io's solid body. Imagine squeezing a rubber ball over and over. Io's interior is likewise kneaded by Jupiter's tidal forces, generating immense heat through friction. That heat melts Io's interior and powers its prodigious volcanoes. In effect, Io is caught in a gravitational tug-of-war. Jupiter's pull and the tugs of its sibling moons have made Io into a tortured, molten world. It's a place of constant eruption, where the sky is often darkened by volcanic plumes and the ground is coated with sulfur snow. If one could hover just above Io's surface, one would see fountains of sulfur spewing upward, and perhaps lightning-like flashes as volcanic material interacts with Jupiter's magnetic field. Io is a dramatic example of how alive a moon can be, when subject to extreme gravitational forces. Moving outward, the next moon is Europa, a world that, at first glance, couldn't be more different from Io. Europa's surface is bright and smooth, like a cracked eggshell of ice. It shines white with slight tan and reddish streaks. These streaks are Europa's signature feature: long, curving fracture lines, some thousands of kilometers in length, that crisscross the entire moon, often intersecting in complex networks. They give Europa the look of a giant marble veined with brownish cracks. When Voyager and later the Galileo spacecraft photographed these lines up close, scientists realized they resemble features on Earth's Arctic seas, ice flows that have fractured and shifted. It appears that Europa's surface ice has broken apart in the past, with pieces pivoting or moving slightly and then refreezing. Very few large craters mar Europa. Its surface is young, geologically speaking. All of this points to an astounding conclusion. Beneath Europa's ice shell lies a global ocean of liquid water. Europa, though smaller than our moon, likely holds more water in its hidden ocean than all of Earth's oceans combined. The same tidal forces that heat Io are at work on Europa, though to a gentler degree, warming its interior just enough to maintain a deep ocean beneath, perhaps 20-30 kilometers below the surface, and perhaps even occasional eruptions of water through the ice. The reddish-brown material lining Europa's cracks might be minerals or organic compounds from the ocean below, deposited on the surface when water squeezed up and froze. Hubble Space Telescope observations have even caught faint ultraviolet glows and blurs at Europa's limb that could be water vapor plumes, geysers like those on Saturn's moon Enceladus, but more intermittent. If those plumes are real, they offer tantalizing direct access to Europa's ocean. Europa's ocean is a place of enormous interest, because wherever we find liquid water on Earth, we find life. On Europa, the ocean floor might have hydrothermal vents, hot springs gushing upward from the rocky core into the seawater, potentially providing chemical energy that could support life forms. Europa's ice layer insulates the ocean from the deadly vacuum and radiation of space. In the utter dark beneath the ice, maybe there are Europan organisms thriving near warm vents, utterly oblivious to the alien sky above. We simply don't know, but the possibility has made Europa a prime target for future exploration. Already, plans are underway. A spacecraft, Europa Clipper, is set to launch soon, which will perform dozens of close flybys, mapping the ice and searching for plume activity. And scientists even imagine a future lander that could drill through the ice or sample fresh deposits. Europa epitomizes the concept of a moon as a world of its own, not a dead satellite, but a potentially life-bearing ocean planet in miniature. The third of Jupiter's big moons is Ganymede, and it breaks records. Ganymede is the largest moon in the entire solar system, bigger in diameter than the planet Mercury. If Ganymede orbited the Sun rather than Jupiter, one might have called it a planet in its own right. Ganymede is a mix of rock and ice by composition, and it has a unique distinction. It is the only moon known to generate a magnetic field of its own. Within Jupiter's immense magnetosphere, Ganymede has a smaller magnetosphere, a bubble of magnetic influence, carved out by Ganymede's internal dynamo. This implies Ganymede has a molten metallic core, likely iron, churning away to create a magnetic field, much as Earth does. When the Galileo probe measured Ganymede's magnetic field, it was a surprise. It hinted that Ganymede is far from an inert ball of ice. The surface of Ganymede tells a story of a complex geological past. There are dark regions saturated with craters, ancient terrain, essentially dirty ice that has been frozen solid for eons. Then there are lighter regions with intricate grooves, ridges, and patterns, swaths of terrain that look like they were deformed or resurfaced later. These grooved terrains may have formed by tectonic-like processes. Perhaps the crust was stretched and new icy material welled up, or by tidal heating effects early in Ganymede's history. Ganymede likely also has a hidden ocean beneath its surface, although deeper down than Europa's. Galileo spacecraft data, and more recently, Hubble telescope observations of Ganymede's auroras suggest a conductive layer, probably salty water, lies between the ice crust and the rocky mantle. So Ganymede could have a sandwich-like internal structure, rock at the center, a layer of warm water or slush above that, then a thick, icy mantle and crust on top. Imagine the variety of environments within: a metal core with a magnetic dynamo, a deep ocean under high pressure, perhaps studded with ice ceiling formations, and a surface that has seen ancient cratering and more recent geological upheavals. Ganymede even has a thin atmosphere of oxygen, extremely tenuous, nothing like what we breathe, but detected through its influence on Ganymede's auroral glow. This oxygen is likely produced by sunlight and charged particles hitting the surface ice, splitting water into oxygen and hydrogen. The lightweight hydrogen escapes, leaving O2 behind. It's another parallel with Earth, which has oxygen from life, whereas Ganymede's is from chemistry. If we could stand on Ganymede, with a spacesuit, of course, we might see Jupiter as a colossal presence in the sky, 3 times wider than our moon appears to us. And we'd feel the tug of Ganymede's magnetic field, interacting with Jupiter's, perhaps auroras in the sky, or a constant drizzle of particles falling to the surface. Ganymede is a transition point, a moon behaving in many ways like a planet, with a rich interior and history. The 4th Galilean moon, outermost of the big ones, is Callisto. Callisto is a survivor from the ancient past, a world that seems to have done little internally for billions of years. Its entire surface is blanketed in impact craters, so many that they overlap and form palimpsests of one another. In photographs, Callisto appears as a mottled, brownish-grey sphere, with bright white spots marking the youngest crater rays. Unlike Io, Europa, and Ganymede, Callisto isn't part of the resonance dance. It orbits too far out to be in the 1-2-4 rhythm, and so it largely escapes the tidal flexing that affects the others. As a result, Callisto never heated enough internally to completely differentiate. Its interior may still be a mix of rock and ice, or drive major geologic resurfacing. It's often dubbed a dead moon geologically, but that doesn't mean Callisto is uninteresting. In fact, as a time capsule, it's extremely valuable. Its ancient craters and surface chemistry preserve a record of conditions in the early outer solar system. One enormous impact basin on Callisto, Valhalla, has concentric rings spreading thousands of kilometers, a frozen ripple from a colossal ancient collision. The sheer density of craters on Callisto's icy plains suggests that, for whatever reason, internal processes never erased them. Interestingly, some evidence hints that Callisto too might have a very deep, sluggish subsurface ocean, perhaps a layer of salty water more than 100 kilometers below the surface, indicated by how Callisto interacts with Jupiter's magnetic environment. But if it exists, that ocean is likely static and cold, a far cry from Europa's or Enceladus's. Callisto's surface materials have been chemically altered by ages of radiation and impacts, giving it a darker hue. It lacks the bright youthful luster of Europa or the dynamic volcanoes of Io. Instead, Callisto offers a tranquil, if desolate, visage, a world that reached an equilibrium and then faded into long cosmic quiet. If one day humans venture to Jupiter's moons, Callisto might actually be an attractive base. Precisely because it's geologically inert and far from Jupiter's strongest radiation belts, it would be safer and more stable for human outposts than the more active inner moons. These 4 Galilean moons, Io, Europa, Ganymede, Callisto, together form a kind of miniature solar system around Jupiter. 3 of them are in a resonant rhythm that ties their fates together, while the 4th stands just outside that chord, solitary and pockmarked. They taught us early on that moons can be as fascinating as planets, and in some cases, more so. Jupiter, however, has dozens of other moons beyond these 4. Most of those are much smaller, irregularly shaped rocks that likely originated as captured asteroids or broken off fragments of collisions. They orbit at various distances. Many ride in packs that share similar orbits. For instance, Jupiter has a gaggle of distant moons that orbit in the opposite direction of the Galileans and opposite to Jupiter's rotation. These are retrograde captured objects, names like Pasiphae, Carme, Ananke, and so on, each only a few kilometers across. They may be remnants of a once larger captured moon that got shattered. Closer in, Jupiter has some inner moons like Amalthea, Thebe, Adrastea, and Metis that are small, tens of kilometers, and orbit very near the planet, zipping around faster than Jupiter rotates. These inner moons actually help maintain Jupiter's faint ring system by supplying dust from meteoroid impacts on their surfaces. Amalthea, reddish and irregular, is large enough, 250 parsecs, to have been discovered in the 1800s by telescope, but the rest were unknown until space probes or modern telescopes found them. With every improvement in our observational capability, Jupiter seems to add another moon to its count. Each is a little world tugged into the giant planet's gravitational embrace. They illustrate how rich a planetary system can be. Some moons were born with Jupiter, like the Galileans, forming out of the disk of gas and dust around young Jupiter. Others were snagged later. From fiery Io, near Jupiter's blazing radiation belts, to lonely Callisto at the fringes, and the tiny rock clusters beyond, Jupiter's moons together create a cosmic ballet around the solar system's largest planet. 400 years ago, we learned not everything orbits Earth. Today, we know that around Jupiter, almost everything orbits it. If our eyes were keen enough, we'd see a second miniature solar system in our night sky, circling that bright point that is Jupiter. Leaving Jupiter's domain and traveling outward, we come to Saturn, the ringed jewel of the solar system. And Saturn too carries a great entourage of moons, different in detail from Jupiter's, but equally fascinating. Saturn's known moons currently number over 100. 83 had confirmed orbits by the end of the Cassini mission, and more have been found since. They range from giant Titan, which is larger than Mercury, down to tiny moonlets, only a kilometer or so in size, embedded in the rings. Many of Saturn's moons are icy, bright objects. Some are darker and likely coated in dust or organic material. They present an astonishing variety of appearances and environments, truly a cabinet of wonders. First and foremost is Titan, Saturn's largest moon and the second biggest moon in the solar system, after Ganymede. Titan is often described as a world with Earth-like traits, and for good reason. It is the only moon with a dense atmosphere. So dense, in fact, that at Titan's surface, the air pressure is about 1.5 times that of Earth's at sea level. Titan's air is mostly nitrogen, like Earth's, but laced with methane and complex hydrocarbons. This thick orange haze shrouds Titan's surface completely, so for decades after its discovery, Titan's face was hidden from view. In 2004 to 2005, however, the Cassini spacecraft and its companion Huygens probe lifted that veil. What they revealed astonished scientists. Titan has liquid lakes and rivers on its surface. It has weather, clouds, even rain. But it's far too cold on Titan, 179 degrees C on the surface, for liquid water. Instead, Titan's hydrological cycle is based on liquid methane and ethane. In Titan's skies, methane clouds gather and occasionally sprinkle methane rain. The rain falls onto an icy crust, water ice as hard as rock, and flows, carving channels and rivers that lead into lakes and seas of liquid hydrocarbons. Cassini's radar mapped seas near Titan's north pole, great expanses of liquid methane-ethane, one larger than Lake Superior. Huygens, the European probe that parachuted to Titan's surface in January 2005, actually landed on a slushy floodplain dotted with rounded ice pebbles, presumably shaped by flowing liquids. It sent back images from the ground, a dim orange sky, and a horizon of smoothed ice rocks, and a clay-like surface that had been wet not long before. Huygens detected moisture in the soil, likely from a recent drizzle of methane. Titan's atmosphere and weather cycle make it uncannily like Earth in outline. There are even likely seasonal changes, with methane rainstorms more frequent in some seasons. Indeed, Cassini saw evidence of one-off torrential downpours causing flash floods and new dark areas appearing, presumably temporary wet spots. But Titan's water is methane, its rocks are water ice, and its sand is likely grains of complex organic material precipitated from the atmosphere. It's as if we have a frozen twin of Earth's past. Some analogies can be drawn to early Earth, though the chemistry is different. Beyond its surface lakes, Titan likely has more surprises underneath. Gravity readings and Titan's rotation suggest Titan hides a subsurface water ocean as well, deep below an ice shell. Thus, Titan might have two habitats: a frigid surface with exotic methane-based chemistry, and a warmer interior ocean of liquid water, perhaps mixed with ammonia, as antifreeze. While life, as we know it, would struggle on Titan's surface, too cold for liquid water, and in liquid methane, biochemistry would be very slow, the interior ocean might be more hospitable. We simply don't have the data yet to know. What we do know is that Titan is remarkably rich in organic chemistry. Sunlight breaking apart methane in the atmosphere creates a wealth of complex molecules that drift down as an orange smog. Titan's surface might be coated in thick organic sediments, a treasure trove of prebiotic chemistry, the kind of molecules that, on Earth, led to the origin of life. This makes Titan extremely compelling to scientists. It's why NASA is planning the Dragonfly mission, a robotic rotorcraft that will launch in the mid-2020s and, by the 2030s, arrive at Titan and actually fly in its dense air from place to place, exploring different locales, dunes, perhaps a dry lakebed, maybe even reaching one of the smaller lakes. Dragonfly will sample Titan's surface chemistry and assess its habitability, effectively playing the role of a wandering chemical lab on this alien world. No other moon has a mission like that on the books. But Titan, unique and complex, beckons us in a special way. It's not just a moon, it's a world with an atmosphere and weather, a cold mirror of Earth in the outer solar system. Saturn hosts another moon that has reshaped our understanding of where life might exist. Tiny Enceladus. Enceladus is a small, bright ice moon, only about 500 kilometers across, that orbits in the midst of Saturn's diffuse E-ring. For a long time, Enceladus was just a shiny dot. Then, in 2005, the Cassini spacecraft discovered that Enceladus is geologically active. At Enceladus's south pole, Cassini spotted enormous plumes of water vapor and ice particles gushing from fissures, nicknamed tiger stripes, in the moon's crust. Geysers on a moon that small. It seemed unbelievable, but there it was. Enceladus was spewing its guts into space. These cryovolcanic plumes form a giant thin halo of fine ice dust around Enceladus, replenishing Saturn's E-ring continuously. Cassini flew through the plumes multiple times, essentially tasting the vapor. It found water, of course, but also organic molecules, various gases, salts, and tiny grains of silica. Those silica grains were a crucial clue. They likely form when hot water reacts with rocky minerals. That implies Enceladus has a hot rocky core in contact with liquid water. In other words, hydrothermal vents on an ocean floor. Yes, Enceladus too has an internal ocean beneath its icy crust, a global ocean of liquid water sandwiched between the core and surface ice. Enceladus is essentially an icy shell with a warm ocean inside and a rocky core that probably provides the heat and chemicals via tidal heating from Saturn's gravity, plus maybe some radioactive decay warmth. It's like a mini Europa, but in some ways even more accessible. Enceladus conveniently jets its ocean out into space for us. The ongoing geysers mean we could, theoretically, fly a probe right through and analyze for complex organic compounds, or even signs of microbial life swimming in Enceladus's ocean. Unsurprisingly, Enceladus shot to the top tier of possible abodes for life beyond Earth after this discovery.
Visually, Enceladus is stunning. Its surface, especially in the south polar region, is young and shiny, continuously resurfaced by falls of plume snow. The tiger stripe fractures are warmer than their surroundings. Cassini measured their temperatures. They were much higher than the frigid 200 degrees C background, indicating heat leaking from within. During Cassini's closest flybys, it actually saw curtains of vapor and icy particles backlit by the sun, a sure sign of active venting. The plume extends hundreds of kilometers into space. It's estimated that about 200 kilograms of water vapor are lost every second through these vents, a huge amount for such a small moon. Yet Enceladus has likely been erupting for millennia or longer. Tidal interactions with Saturn, and possibly a resonance with another moon, Dione, provide energy that keeps its interior warm enough to maintain liquid water. The entire south polar region of Enceladus seems to be a geologically unique province, crisscrossed by young fractures and free of large craters, clearly a hotspot above the internal ocean. By contrast, Enceladus's mid-latitudes and northern areas are older and heavily cratered, suggesting that the activity is focused in the south. No one is yet sure why only the South Pole is active. One idea is that a past impact or uneven distribution of heat caused a sort of cap of warmth down south. Whatever the cause, Enceladus is essentially a natural space fountain, spraying its ocean into the void and giving us a direct glimpse into an environment that could be habitable. As a result, there is great eagerness to go back. Future mission concepts include an Enceladus Life Finder probe, or even a sample return that would collect plume particles and bring them to Earth's labs. If, one day, we discover microorganisms or biosignatures in those salty ice grains from Enceladus, it would rank among the most profound discoveries in history. All from a tiny moon that, not long ago, we assumed was inert. Enceladus teaches us that even small moons can be extraordinary.
Saturn's inventory of moons doesn't end with Titan and Enceladus. There are dozens more, each with quirks. One of the most intriguing is Iapetus, a moon of moderate size, about 1,470 kilometers across, that has a two-toned appearance. The leading hemisphere of Iapetus, the side that faces forward in its orbit, is as dark as coal, while the trailing hemisphere is bright as snow. This gives Iapetus a striking yin-yang look. One half of the moon literally 5 to 10 times darker than the other. The dark material is thought to be debris, possibly dust from Phoebe, a distant retrograde moon of Saturn, that splattered onto Iapetus, or residue of icy materials that sublimated and migrated away, leaving a coating of complex organics behind. In addition to its color dichotomy, Iapetus sports a startling physical feature, a colossal ridge running exactly along its equator, wrapping much of the moon like the seam of a walnut. Some sections of this ridge reach 20 kilometers in height. It makes Iapetus look like two icy halves stuck together. The origin of this equatorial ridge is still debated. One hypothesis is that Iapetus long ago had a ring of debris around it, perhaps from a collision, and that ring rained down along the equator, building up the ridge. Another idea is that Iapetus rotated faster in the past, with a shorter day, and the equatorial bulge froze in place when the moon's interior cooled and solidified. Then, as the rotation slowed, the bulge became a towering ridge. In any case, no other known moon has such a feature. Iapetus orbits far from Saturn, quite isolated compared to most of Saturn's moons, almost 3.5 million kilometers out, and takes over 79 days to go round. In the Saturnian sky from Iapetus, Saturn would appear small. Iapetus is a bit of a loner, a mysterious one at that. Another noteworthy Saturnian moon is Rhea, the second largest of Saturn's moons, about 1,528 kilometers across. Rhea is a heavily cratered, cold classic ice moon, but with a twist. In 2010, Cassini detected a very tenuous atmosphere around Rhea,
composed of oxygen and carbon dioxide. This was the first time an oxygen atmosphere was found at a world other than Earth. Later, we discovered O2 on Europa and Ganymede 2 in trace amounts. Of course, Rhea's atmosphere is exceedingly thin. A human would not notice it, but its existence means that chemical reactions are happening at Rhea's surface. The likely source of the oxygen is Saturn's strong magnetic field trapping charged particles that constantly bombard Rhea. When these high-energy particles strike the icy surface, they can liberate oxygen from water ice, a process called radiolysis. The carbon dioxide's origin is less clear, perhaps from trace organics in the ice being oxidized, or from dry ice trapped in Rhea's water ice. Rhea's surface shows hints of ancient tectonics. Some wispy white streaks on the trailing hemisphere turned out, on closer inspection by Voyager in the 1980s, to be bright ice cliffs, likely fractures where subsurface cleaner ice pushed out. But overall, Rhea seems geologically inactive now. Intriguingly, a few years before the atmosphere find, there was speculation, based on charged particle data, that Rhea might even have a tenuous ring system of its own, a set of thin equatorial rings of debris. It would have been the first moon known to have rings. Follow-up imaging didn't conclusively show anything, and the idea remains unproven. If Rhea had rings, they would be extremely sparse. Still, it's a reminder that moons can blur the line between what distinguishes a planet, with rings and moons, and a moon. Nature is creative. Then there are Dione and Tethys, mid-sized moons of Saturn, around 1,100 kilometers across. Dione has bright wispy streaks across one side, once thought to be ice volcanism, but actually they are enormous bright cliffs, revealed by high-resolution Cassini images, marking tectonic fractures where fresh ice was exposed. Dione likely had internal activity in the past. There is some evidence, gravity measurements. It might even have a deep subsurface ocean now, though not certain. Its surface shows regions where tectonic forces pulled the crust apart, creating canyons and letting cleaner ice resurface the area. Tethys, on the other hand, is very ancient looking, dominated by a huge impact crater named Odysseus that spans nearly 2/5 of its diameter, a colossal basin that almost shattered the moon. Tethys also has a giant valley called Ithaca Chasma, running roughly north-south for 2,000 kilometers, possibly formed as the crust cracked during cooling or when the big impact occurred. Both Dione and Tethys are largely ice, and both are locked in synchronous rotation around Saturn, keeping one face towards Saturn always. These moons also participate in orbital resonances. Tethys is in a 2-1 resonance with a smaller moon, Mimas, and Dione in a 2-1 with Enceladus. These gravitational relationships help maintain certain orbital spacings and may have once contributed to heating, especially Dione's resonance pumping Enceladus's orbit. Mimas, the innermost of Saturn's major moons, just 396 kilometers across, is often noted for its appearance. One huge crater, named Herschel, forms a distinctive round gouge so large it makes Mimas look like the Death Star from Star Wars. That crater is about 140 kilometers wide. If the impact had been much harder, Mimas might have been split apart. The impact made the moon ring like a bell. Interestingly, when scientists measured Mimas's rotation, they found a slight oscillation that was difficult to explain. One hypothesis, still controversial, is that Mimas might hide a tiny internal ocean or a weirdly shaped core causing an unexpected wobble. It would be surprising, given Mimas's small size and heavily cratered, seemingly inactive surface, but the data haven't fully ruled it out. It's a reminder that even the most innocuous-looking moon could harbor secrets below. For now, Mimas is regarded as a solid ice rock ball, heavily cratered. Aside from giant Herschel, many smaller craters give it a dimpled look, and it serves as a gravitational shepherd of Saturn's rings. In fact, Mimas is responsible for clearing out the Cassini division, the biggest gap in Saturn's main rings. Its gravity resonates with particles there, in a 2-1 resonance, ejecting them from that orbit over time. So even a small moon like Mimas can impose grand structure on a planetary ring system. Beyond the major moons, Saturn boasts a zoo of smaller moons, each contributing to the complex ballet of ring and moon dynamics. Tiny Pan and Daphnis, for instance, are little moons that inhabit gaps within Saturn's rings, the Encke gap and Keeler gap, respectively. As they orbit, these moons act as shepherds, their gravity nudging ring particles and keeping the gaps open. Pan is particularly adorable. Images show it has a flattened shape with a prominent equatorial ridge, making it look like a flying saucer or a piece of ravioli. Likely, Pan has accreted a skirt of fine ring material around its middle. Atlas is another ring-adjacent moon with a similar look. Then there are Prometheus and Pandora, a duo that shepherd the narrow F ring from either side, their repeated pulls corralling the ring particles into a tight band, while also creating kinky streamers and gores in the ring as they tug unevenly. Janus and Epimetheus form a unique pair. They share almost the same orbit and actually swap positions every few years in a do-si-do, a gravitational dance of co-orbital moons. Such an arrangement is extremely rare. They essentially trade orbits each time they approach, ensuring they never collide. And Janus Epimetheus were the first known co-orbital moons. Farther out, Saturn has a collection of irregular moons, captured objects with inclined, often retrograde orbits, much like Jupiter's outer moons. One of these is Phoebe, a dark, charcoal-like body, about 200 kilometers wide, that orbits opposite to Saturn's rotation, in a distant orbit. Phoebe is believed to be a captured Kyper belt object, or something from that distant population, imported into Saturn's gravity well. Material from Phoebe is thought to be the source of the mysterious dark coating on Iapetus's leading face. Dust from impacts on Phoebe migrates inward and eventually splatters on Iapetus. In this way, moons can affect each other across vast distances through dusty footprints. Altogether, Saturn's moons form an elaborate system of interactions with the rings and with Saturn's magnetosphere. The Cassini mission, 2004 to 2017, gave us an intimate look at this system, and every moon it examined turned out to have something unique. Enceladus with its plumes, Titan with its lakes and thick air, Iapetus cut in two-tone, Hyperion, a sponge-like chaotically tumbling moon resembling a giant honeycomb, even tiny moons like Methone, which are smooth, egg-shaped bodies, perhaps covered in fluffy, powdery material. One comes away with a sense that the Saturnian system is a kaleidoscope of natural experiments, each moon a slightly different mix of ingredients and history. If Jupiter's moons are like a quartet of well-studied characters, Saturn offers an entire ensemble cast, some playing major roles, others cameos, all contributing to the dynamism of the planet's environment. Continuing outward, we reach Uranus, the ice giant tipped on its side. Uranus's extreme axial tilt, 98°, means its moons follow a bizarrely skewed path. They orbit around Uranus's equator, which is essentially vertical relative to the planet's motion around the Sun. So the Uranian moon system is like a tilted disk rolling along with Uranus. The 5 main moons of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, are mid-sized icy worlds, all locked in synchronous rotation, showing the same face to Uranus. And all relatively dark, they don't reflect as much sunlight as Saturn's bright icy moons do. We know comparatively little about them, as only Voyager 2 has ever flown past, in 1986, giving us single snapshots of each. But those snapshots revealed astonishing geology on some. Miranda is the smallest of the 5, about 500 kilometers across, and the most bizarre. It looks as though a child tried to glue together mismatched pieces of planet. Parts of Miranda's surface are extraordinarily grooved and chevroned, giant coronae structures that have no counterpart elsewhere. One region has a huge V-shaped ridge and trough feature, nicknamed the chevron. Others have oval racetrack-like patterns of grooves. Alongside these strange regions are cratered highlands that seem more ancient. Miranda also boasts cliffs up to 20 kilometers high. The famous Verona Rupes is perhaps the tallest known cliff in the solar system. The current theory is that Miranda underwent partial differentiation and tectonic activity, perhaps driven by tidal heating when Uranus might have captured it in a resonance at some point, that caused it to nearly come apart, or at least shift dramatically. Another hypothesis, more dramatic, is that Miranda was shattered by a massive impact and reassembled. In any event, Miranda's surface is the most varied, patched-together landscape of any moon its size. Despite being so small, which usually means geologically dead, Miranda clearly experienced major upheavals. Now it orbits quietly, but it hints at an interesting past. Perhaps it was once in orbital resonance with Umbriel or Ariel that induced internal heating. Ariel and Titania show signs of relatively recent resurfacing. Ariel, especially, has fewer craters than Umbriel or Oberon, and has many large canyons and smooth, floored valleys. The bright cliff edges and the topology suggest Ariel's icy crust was tectonically active. Maybe it warmed and partially melted, repaving sections of the surface. Titania, the largest Uranian moon, about 1,580 kilometers across, has a network of rifts and faults, including the Great Valley, Messina Chasm, about 1,500 kilometers long and up to a few kilometers deep. This suggests Titania expanded slightly, as Ice 2 in the interior might have shifted to Ice 1, expanding volume, and cracked its crust. Both Ariel and Titania might conceivably hold thin subsurface oceans if there's enough radioactive heat inside, or if some ammonia is mixed in to lower the freezing point, but that's speculative. Umbriel and Oberon, in contrast, appear more ancient and heavily cratered. Umbriel is the darkest of the five, a charcoal-colored orb with an oddly bright ring on one crater, possibly a deposit of fresh frost from an impact. It seems to have been mostly inert for a long time. Oberon, the outermost major moon, has a mix of craters and some signs of geological activity, like a few large faults or graben. One of Oberon's notable features is a mountain sticking out of a crater, perhaps an uplift of ice from an impact. All five of these moons orbit in the same plane, and interestingly, that plane, Uranus's equator, currently lies nearly perpendicular to the Sun. This means during parts of Uranus's 84-year orbit, the moons experience 42 years of continuous daylight, followed by 42 years of continuous darkness. During Voyager 2's flyby, Uranus's south pole and the southern hemispheres of the moons were in full sunlight. The northern halves were dark. Now, decades later, the illumination has flipped. Such long seasons could affect the moons, for instance, causing subtle warming and refreezing of surface ices, movements of tenuous atmospheres, if any exist. One of the big mysteries left by Voyager is that none of Uranus's moons showed clear evidence of internal heating at present. Yet, given how unique Miranda is, and how Ariel and Titania have signs of resurfacing, one wonders if perhaps in the past, some resonances or tidal interactions, maybe when Uranus's spin axis precessed differently, or if the moons migrated outward, caused heating episodes. Beyond the Big Five, Uranus has a myriad of smaller moons down to 20 kilometers across, many discovered only in the past few decades by improved telescopes or by Hubble. They have whimsical Shakespearean names: Puck, Sycorax, Portia, Juliet, Cupid, etc. Some of the inner ones are in orbital dances that exchange energy and maintain spacing, similar to Saturn's ring shepherds. And like Jupiter and Saturn, Uranus also has a cohort of distant irregular moons captured into inclined or retrograde orbits. Uranus's moons are among the least explored in the solar system. No spacecraft has orbited Uranus to give them a closer look, but they present an intriguing case study. How does an extreme axial tilt affect the evolution of moons. They might have experienced tidal heating in the past. Miranda's crazed surface is evidence of something. Perhaps some still have liquid layers deep down. We just don't know yet. Future missions. A Uranus orbiter has been recommended by planetary scientists for launch in the 2030s. Will hopefully shed light on these sideways moons. Finally, we reach Neptune, the last of the giant planets, and here we encounter one of the strangest moons of all, Triton. Triton is unique among large moons because it orbits Neptune in a retrograde direction, opposite to Neptune's rotation, and at a fairly steep inclination to Neptune's equator. This immediately tells us Triton was very likely not formed around Neptune, but was captured. Triton is about 2,700 kilometers in diameter, similar in size and composition to Pluto. In fact, Triton is probably a former Kyper belt dwarf planet that strayed too close to Neptune eons ago and was snared by its gravity. The capture of such a large object would have been a violent event. Triton's original orbit would have been highly eccentric after capture, causing tidal friction that could have melted a large part of Triton's interior. Neptune's original moons, if it had a regular satellite system, might have been destabilized and lost in the process. Over time, Triton's orbit circularized and shrank due to tidal interactions. Today, Triton orbits Neptune in a close, tight retrograde loop every 5.9 days, and Neptune's gravitational grip keeps Triton's rotation locked. 1 Triton day equals 1 Triton year, always showing the same face to Neptune. When Voyager 2 flew by Neptune and Triton in 1989, it revealed an active and youthful surface that stunned scientists. Portions of Triton are a pinkish-white icy plains, others are a mottled cantaloupe terrain of fused depressions. Few impact craters were seen, implying the surface is relatively young, perhaps no more than a few 100 million years old in places. Most surprising of all, Voyager's cameras caught sight of dark geysers erupting from Triton's surface. In Triton's thin nitrogen atmosphere, surface pressure only 1/70,000th of Earth's, they saw black streaks arcing up from the ground and then blown downwind, likely by gentle winds. These were cryogeysers, probably driven by solar heating of translucent nitrogen ice on Triton's surface. Here's how it works. Sunlight penetrates a layer of clear frozen nitrogen, warms material a few centimeters below, and that causes sublimation, trapped gas, which then finds a crack to explosively escape, carrying darker particles, like soot or organic compounds, with it, which then fall and streak the surface. Triton, therefore, has active nitrogen volcanism of a sort, powered not by internal heat, but by external sunlight, a very peculiar mechanism, unique to Triton so far. Beyond those geysers, Triton's landscape shows signs of tectonic movement and perhaps cryovolcanic resurfacing in certain areas, dubbed smooth plains. Voyager saw what looks like frozen slurry that had flooded and refrozen, akin to lava fields, but of icy material. Triton is exceedingly cold, around 235 degrees Celsius, just 38 K. Its surface is composed of a mix of nitrogen, methane, and carbon monoxide ices, with water ice making up much of its crust and interior. It has polar caps of nitrogen and methane ice. Voyager saw a bright southern cap. It was summer in Triton's southern hemisphere at the time, and likely there's a northern cap now that the seasons have changed. Triton's thin atmosphere includes nitrogen, the primary constituent, a bit of methane, and likely some carbon monoxide. These can form thin hazes and clouds. Voyager actually observed a delicate pinkish haze, layers up to 30 kilometers above Triton, likely photochemical smog from methane, analogous to Titan's haze, but far thinner. This atmosphere can freeze onto the surface when winter comes to one pole or the other, meaning Triton undergoes a sort of atmospheric collapse and rebirth with its seasons. Under Triton's surface, given its relatively large size and the likelihood of past tidal heating from capture, it's hypothesized that Triton might still have a subsurface ocean, perhaps kept liquid by residual heat and antifreeze like ammonia. If so, Triton could harbor conditions for life in that interior ocean similar to Europa or Enceladus, though we have no direct evidence of it yet. Over the long term, Triton is spiraling inward toward Neptune. Millions of years from now, very roughly 3.6 billion years, Triton may reach Neptune's Roche limit and be torn apart, possibly forming a spectacular ring around Neptune. But that is far in the future. Neptune's other moons are comparatively small and faint. Proteus, about 420 kilometers across, is the largest after Triton. It's a darkly coated irregular shape. Voyager saw it as a lumpy, heavily cratered object. It's so large that one might expect gravity to have made it spherical, but Proteus is right at the edge of that transition and apparently never melted enough to round itself. Proteus orbits close to Neptune, just outside the narrow rings Neptune has. Nereid is another interesting one. Discovered in 1949 from Earth, it has a very elongated orbit around Neptune, which suggests it might be a surviving original moon that was severely perturbed when Triton was captured. Nereid is about 340 kilometers in size and rotates chaotically. Then there are several much smaller moons discovered mostly in the 21st century, with help from Hubble and large telescopes. Names like Despina, Galatea, Larissa. Actually, Larissa was seen by Voyager. It's about 200 kilometers. And farther out, Halimed, Sao, Laomedea, Neso, etc., which are only tens of kilometers across or less. One tiny moon, Hippocamp, about 35 kilometers, was only discovered in 2013. It orbits very close to Proteus and may actually be a fragment knocked off Proteus by an ancient impact, a baby moon born from a collision. The fact that even Neptune, way out in the dim reaches, with its chaotic history, holds a retinue of at least 14 moons reinforces that satellite systems are a common part of planets. Our tour of the solar system's moons wouldn't be complete without venturing to the very edge, to the dwarf planets of the Kyper belt, which themselves have moons. Pluto, once the 9th planet, and now the archetype of a dwarf planet, has a complex little system of its own. Pluto's largest moon, Charon, was discovered in 1978, and it's so big, relative to Pluto, half Pluto's diameter, an eighth its mass, that Pluto and Charon together orbit a point in space between them, like a binary planet. Charon's gravity has locked Pluto in place, just as Pluto's gravity locked Charon. Thus, Pluto and Charon are mutually tidally locked, eternally facing each other as they spin through space. A Pluto day equals a Charon day equals 6.4 Earth days, and that's also the time it takes for Charon to orbit Pluto once. From Pluto, Charon hangs at a fixed spot in the sky, or never rises if you're on the far side. From Charon, Pluto does the same. They are like two dancers holding an unbreaking gaze. Charon itself is about 1,212 kilometers across, and before 2015 was just a fuzzy blob in Hubble images. The New Horizons flyby in July 2015 changed that, revealing Charon's surface in detail. We saw a surprisingly varied terrain. Charon's southern hemisphere is covered in large craters and older surfaces, while its northern hemisphere has a massive dark reddish-brown cap at the pole, quickly dubbed Mordor informally. Across Charon's middle is an enormous belt of chasms, a giant system of canyons and scarps stretching more than 1,000 kilometers, with some cliffs 7 to 9 kilometers tall. This tectonic trench system suggests that at some point Charon's interior expanded, likely as an internal ocean of water froze and expanded, cracking the crust above. When water freezes, it takes up more volume, and on a global scale this could push the surface outward, causing the moon's crust to fracture extensively. The result? Charon's face bears a dramatic scar of that event. North of this belt, New Horizons saw smoother plains with fewer craters, notably a region called Vulcan Planitia. This area might have been resurfaced by cryovolcanism, essentially ammonia-rich water that oozed up and spread out as a kind of cold lava, filling in craters. It could be that after Charon's ocean began to freeze and the crust cracked, there was some upwelling of liquid that created a renewed, smoother surface in places. Charon's polar dark region, meanwhile,
is thought to result from gases escaping Pluto. During Pluto's long winter, its atmosphere collapses onto the surface, but during the relative warmth of perihelion, some of it escapes Pluto's weak gravity. Charon, orbiting nearby, can capture some of these molecules, like methane. At Charon's poles, during its long winter night, those gases freeze onto the surface. There, ultraviolet sunlight eventually chemically alters the methane ice into heavier hydrocarbons and tholins, complex organics with reddish color. Over millions of years, this process painted Charon's poles that deep red-brown hue. Essentially, Charon has stolen a bit of Pluto's escaping atmosphere and turned it into a paint for its own surface.
Pluto itself is a wonderland, a great heart-shaped expanse, Tombor Regio, of which the western lobe is Sputnik Planitia, a vast basin of nitrogen, carbon monoxide, and methane ices that is notably free of craters. This indicates it's geologically very young, perhaps less than 10 million years old. The surface there is divided into polygonal cells about 20 to 40 kilometers across, which appear to be convection cells. The nitrogen ice warmed slightly from below, churning very slowly like a boiling pot, albeit on a timescale of tens of thousands of years per cycle, bringing fresh material up in the center of cells and pushing older ice to the edges where it cools and sinks. This process erases craters and produces a constantly renewing icy plain. Sputnik Planitia is thought to sit in a deep basin, likely caused by an ancient impact. Intriguingly, this basin is almost exactly opposite Pluto's side that faces Charon. That hints that the basin is somehow heavy, perhaps filled with denser material or hiding a subsurface ocean, and that Pluto reoriented, true polar wander, to place that heavy spot on the tidal axis facing Charon, as gravitational interactions prefer. One theory is that there is, or was, a subsurface ocean of liquid water underneath Sputnik Planitia, whose mass, or the way it responds to flexing, helped stabilize Pluto-Charon in their orientation. Pluto also has tall mountains, some over 3 to 4 kilometers high, made of water ice bedrock poking through softer nitrogen and methane ice terrain, and some of those mountains, like Right Mons, have deep central pits, possible cryovolcanoes that erupted a slushy mix in the past. To the north of Sputnik lies a rugged highland of heavily cratered terrain called Cthulhu Macula, dark in color from tholins. There are also weird bladed shapes on some equatorial ridges, perhaps formed by sublimation of methane ice into spiky landforms. And Pluto has a thin, multi-layered atmosphere primarily of nitrogen, which, when backlit by the sun, gleams with blue haze layers. A delicate, ethereal sight, New Horizons captured as it looked back at Pluto after closest approach. Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier, ranging 30 kilometers to 150 kilometers across, and irregularly shaped. They were likely born in the same giant impact that formed Charon. They orbit in a neat resonant hierarchy. Styx, Nix, Kerberos, Hydra are in a 1, 3, and 4, 5, and 6 sequence with Charon, approximately. Curiously, these little moons rotate chaotically. For instance, Hydra spins roughly every 10 hours, but with a wobble that makes the exact rotation unpredictable. This chaos arises because Pluto and Charon's gravitational field is constantly varying as they orbit each other, perturbing the small moons. Imagine trying to spin a top in a gravitational field that changes slightly in orientation. It would be hard for the top to keep stable, so a visiting spaceship might find, say, Nix tumbling end over end rather than smoothly rotating on one axis. The surfaces of these moons are quite reflective, especially Hydra, indicating they're covered in relatively clean water ice. They likely formed from the outer bits of Pluto-Charon's impact ejecta that coalesced into small bodies. All in all, the Pluto system provides a fascinating parallel to the planet-moon systems we've seen closer in. It's like a mini solar system in the deep freeze, complete with a binary planet and an entourage of tiny moons
shaped by a cataclysmic birth and delicate gravitational interplay. We've gone from seeing the moon in our sky, singular and familiar, to realizing that even tiny distant Plutos have multiple moons of their own. Moons, we've learned, are everywhere. And that naturally brings us to the question of exomoons. Moons around planets orbiting other stars. We now know of thousands of exoplanets, and by sheer probability, many should have moons. In our solar system, 6 of the 8 planets have moons, and the 2 that don't are the innermost scorched by the sun. The processes that lead to moons, co-formation in disks around young planets, capture of passing objects, giant impacts that throw off debris, these should also occur elsewhere. For a long time, though, exomoons eluded detection. They are smaller and dimmer than the already faint exoplanets. But astronomers are clever. They look for subtle effects in the data. One method is to watch the transit of a planet across its star and see if there are extra tiny dips or a slight asymmetry that could be caused by a moon either leading or trailing the planet. Another method is to measure slight variations in the timing of transits. A moon's gravity will cause the planet to wobble as they both orbit their center of mass, so the planet might transit a few seconds early or late in a regular pattern, betraying the presence of a companion. In the past few years, tentative signs of very large exomoons have emerged. One candidate is a Neptune-sized moon orbiting a Jupiter-sized exoplanet called Kepler 1625b, about 8,000 light-years away. If that detection is correct, it's still debated. It's an utterly alien scenario. A moon that big, radius Hayamal the size of Neptune, there's nothing like it around our sun. It might almost be a binary planet situation. Another candidate, around the exoplanet Kepler 1708b, also seems to be a giant moon, roughly 2 to 3 times Earth's radius. Why are we finding only giant moons? It could be that our detection methods right now are sensitive only to very large effects. Catching something Earth-sized or smaller is at the edge of our capabilities with current telescopes. The large moons might also be rarer outcomes, maybe even remnants of a double planet capture, or a planet that kept a fellow gas giant as a moon. As of now, no exomoon is confirmed beyond doubt. These signals are intriguing, but require follow-up with perhaps the James Webb Space Telescope or future extremely large telescopes to verify. Scientists are also mindful of selection bias. A habitable zone Earth-like planet could well have a modest moon, perhaps like our moon, but detecting that is far harder than detecting a Neptune-sized moon. So we shouldn't conclude exomoons are all huge just because the 2 candidates are. It's like if the only fish you could catch with your net were the big ones. You might falsely imagine the lake only has big fish. Many researchers suspect that moons as a class are common and diverse out there, likely reflecting what we see here. Lots of small moons, some medium, a few very large relative to their planets. In fact, some exoplanetary systems might have moons larger than Mars, orbiting super-Jupiters, or multiple moons around a super-Earth. The hunt for exomoons is more than a curiosity about numbers. If exomoons exist in habitable zones, they themselves might be abodes for life. Consider a Jupiter-sized planet orbiting its star at the right distance for liquid water. Any large rocky moon around it could have Earth-like conditions, receiving light from the star and perhaps from the planet, reflected light, and experiencing tides that might be gentle or, if orbit is eccentric, enough to warm its interior. Science fiction has often toyed with the idea of habitable moons. Think of the forest moon of Endor in Star Wars or Pandora in Avatar. Nature might actually offer such places. They could have day-night cycles defined not only by their own spin, but also eclipses by their planet. Imagine living on a moon where regularly the giant planet looms in the sky and periodically eclipses the sun entirely, turning day to an eerie twilight as the planet's silhouette and corona cover the sun, a spectacular sight and a normal part of the moon's rhythm. Tides on such a moon might be complex, pulled by both the planet and the distant sun. A large moon around a giant planet might also be shielded by the planet's magnetic field from cosmic rays,
or conversely, bathed in intense radiation if the planet has strong belts, like Jupiter does, which would be harmful for life on Io or Europa's surface. The interplay of factors is complex, but the possibility expands the concept of a habitable zone. It's not just planets we should consider, but moons of big planets too. Future telescopes might detect exomoons by their own atmospheric imprints. For instance, if a moon has a big atmosphere and it transits a star either slightly before or after its planet, perhaps a sensitive instrument like JWST could discern a tiny spectral signature like oxygen or ozone separate from the planets. At present, though, exomoons remain a frontier, one of the few categories of celestial object in the modern era still without a confirmed specimen beyond our solar system. This will likely change as data and techniques improve, and when it does, we will have an even broader context for understanding our own moons. We might learn how common or uncommon arrangements like Earth-Moon are, or whether huge moons commonly form around super-Jupiters, or how often moons survive migratory upheavals that many exoplanets undergo. Each new moon detection will add a piece to the puzzle of planetary system formation. Reflecting on all these diverse moons, from Earth's lifeless but life-enabling moon, to fiery Io and oceanic Europa, to hazy Titan and eruptive Enceladus, to shattered Miranda and retrograde Triton, to Pluto's binary dance with Charon, one cannot help but feel a sense of cosmic kinship. Moons have profoundly shaped the stories of their parent planets, and in Earth's case, the story of life itself. They are not mere afterthoughts of creation. They are active participants in the celestial drama. The relationships between moons and their planets are dynamic. Gravitationally, the moon and planet tug at each other, exchanging angular momentum. Our days lengthen as the moon drifts out. Mars's fate of Phobos is sealed by tides pulling it in. Many moons are locked facing their planet, as if gazing eternally at the giant that dominates their sky. Some, like Pluto and Charon, even lock onto each other in a perpetual mutual stare. These are like cosmic dances, sometimes a waltz in synchrony, sometimes a wild jig, as with chaos of Hyperion or Nyx. From a human perspective, moons also taught us humility and wonder. When Galileo observed Jupiter's moons moving, it was a blow to the egocentric model of the heavens, a key step toward the realization that Earth is not the center of all motion. Moons gave us the first accurate measure of the speed of light. Danish astronomer Ole Rømer used eclipses of Jupiter's moon Io to deduce light didn't travel instantaneously. Our own moon was the first extraterrestrial world visited by humans, and when Apollo 11's Neil Armstrong set foot on it in 1969, the event united humanity in a moment of pride and perspective. For the first time, a being from Earth walked on another world and looked back at our planet rising in the black sky. Those Earthrise photos taken from the moon showed our blue globe in stark relief against space, underscoring both its beauty and fragility. It's often said that our moon keeps memories alive in its dust. The footprints of astronauts remain sharp and undisturbed decades later, and will likely persist for millions of years since there's no wind or water to erase them. The moon, in that sense, is a guardian of human history as well. Culturally, the moon has been a muse for countless generations, inspiring art, poetry, calendars, myths. We project our feelings onto it. Lovers see a symbol of romance in the moonlight. Poets see melancholy or hope. The word lunacy stems from the belief that the full moon could drive people mad or influence behavior. While science finds no strong evidence for that, the notion persists in folklore. What is true is that the moon's cycles were among the most observable rhythms for ancient people. The word month, moonth, reflects its roughly 29.5-day cycle of phases. Even today, many cultures celebrate Lunar New Year's or festivals tied to moon phases. Moons elsewhere may not have such direct cultural roles for us, but just knowing they exist expands our imagination. We can conceive of skywatchers on a distant exomoon, their night sky dominated by the hulking visage of their parent planet. What myths might they spin about that eternal presence? Our exploration of moons has also been a grand human adventure. We've sent probes to fly by or orbit all the planets with moons, and landers to a few, the Moon, Mars's Phobos soon with Japan's mission, Titan's Huygens. Each mission had its moments of awe. The first close images of another world's moon, Mariner 4 seeing craters on Mars's moons, or Voyager 1 revealing volcanoes on Io. The breathtaking complexity of Europa's cracked ice seen by Galileo, or the descent of Huygens through Titan's orange sky, parachuting down for hours and recording the sounds of Titan's winds before touching the pebbled ground. When Cassini dived through Enceladus's plume, essentially sampling an alien ocean, we were doing something both scientifically profound and almost philosophically poetic, tasting the water of a moon's hidden sea like a scout for life beyond Earth. And one day, perhaps in this century, we might actually return samples from such an ocean, or have a lander melt down through Europa's ice, or a submarine drone swim in Titan's methane lakes. These ideas, once purely fanciful, are now discussed in serious engineering terms. In pondering all these moons, one cannot escape a feeling of connectedness, the moon's gentle tug on Earth's oceans, the gravitational embraces and clashes that heat Io or freeze Triton, the subtle orbital resonances that link Io to Europa to Ganymede or that locked Pluto and Charon in co-orbit. It's like a grand choreography governed by gravity. Our solar system is not a collection of isolated planets, but a web of interactions, and moons are the threads weaving much of that web. They cause eclipses and transits, cast shadows and reflect light. When our moon eclipses the sun, we see the sun's corona and have even tested Einstein's theory of general relativity during such events. When Io eclipses Jupiter, slipping into Jupiter's shadow, its volcanoes briefly diminish as the sunlight-driven part of their activity ceases, and auroras dance at Io's poles. Moons, by blocking sunlight or reflecting it, create some of the most beautiful celestial sights. The diamond ring effect of a total solar eclipse on Earth, or the sparkle of the full moon on a calm sea, the very sight we began with. And so we come full circle. The tides that our moon raises, which we noticed in the opening scene at the seashore, tie us intimately to our satellite. That same rhythmic motion of tides is happening in different forms, on moons around other planets, the crust of Europa flexing like a global tide in solid ice, Titan's atmosphere circulating in response to the seasonal tides of solar heating, tiny Mimas locked in a spin-orbit dance with Saturn's rings, raising a slight warp in the rings that we can measure. The language of orbits and tides is universal. It has a music to it. Moons in resonance are literally in a harmonic relationship. Io, Europa, Ganymede, odds 4-2-1, a Laplace resonance that could be set to a beat. In a poetic sense, one could imagine that each planetary system has its own music of the moons. We, with our instruments and spacecraft, have begun to hear these cosmic melodies. As the night deepens here on Earth and the tide slips back, one might look up at our moon and feel a new sense of kinship with the other moons of our solar system. Moonlight on water is a beautiful, gentle thing. It has soothed and inspired humans for ages. Now we know that moonlight is not unique to Earth. Jupiter's moons see the sun as we do, and their surfaces shine under the distant sun. A traveler on Europa would see Earthlight, the glow of Jupiter, and maybe Io or Ganymede in the sky, softly illuminating the Europan night. On the moon, astronauts marveled at Earthshine, lighting the dark portion of a crescent moon, the reflection of our blue planet bathing the lunar night. Everywhere there are moons, there are similar interactions of light and gravity creating subtle beauty. In the end, what do moons mean to us, humanity? They mean we are not alone in the sense that even our planet travels with a companion. They mean that nature often works in pairs or families. Planet and moon, giant planet,
and dozens of moons. Moons remind us that the distinction between planet and satellite can sometimes be a matter of perspective and definition. Is Charon a moon, or part of a binary dwarf planet? If an exomoon is huge enough, would we consider it a planet in its own right? Moons expand the stage on which the drama of the solar system plays out. Not only do we have planets orbiting the Sun, but dozens of subworlds orbiting those planets, each with its own story. To humanity, the Moon, ours, was the first stepping stone away from Earth, and perhaps it will again be a stepping stone if we venture further. Future explorers might use the Moon as a base, or go from the Moon to Mars, and one day to the moons of outer planets. Our lore and language are filled with the Moon. Now our science is filled with moons. Standing on a beach under the Moon's glow, we can feel the connection, the pull of the Moon lifting the tide around our ankles. That same force extends to every moon and planet, a grand tapestry of gravitational embraces. In a way, moons are bridges between the emptiness of space and the surfaces of planets, between solitude and companionship in the cosmic sense. Planets with moons are not alone. They carry little worlds with them, as we carry memories or histories. Jupiter carries a mini solar system of worlds. Saturn carries an entourage that creates its rings and possibly harbors life's precursors. Uranus carries secrets of tipped evolution. Neptune carries a stolen world that still geologically rebels. And Pluto carries the partner that reveals its heart. And Earth carries the Moon, which has through chance and physics given us stable seasons, tides, and a night light, arguably a cradle for life, and certainly a cradle for the human imagination. As the tide now withdraws under the Moon's dominion, and the moonlight stretches its silver road across the sea, we are reminded that our world is part of a much larger family of worlds. Each ripple at our feet is answered by a tug from the Moon, each glint of light a message that we are bound together. And beyond our Moon, dozens of others dance and shine around their primaries, shaping and being shaped. In the silence of the night, if you listen closely with your mind's ear, you might almost sense it. The harmony of moons in their orbits, a serene cosmic music playing across time and space. It is a lullaby and an anthem, a lullaby that has eased human hearts when they gaze at a quiet moonlit sky, and an anthem to the richness and interconnectedness of our solar system. Moons are the ever-present companions of planets and perhaps of life itself, turning loneliness into a dance of two or many. Under the calm, dreamy light of our Moon, we feel that companionship deeply. The Moon and the tide assure us that in this vast universe, there are rhythmic connections we can count on.
Tonight, the Moon's path of light quivers on the water with the ocean's breath. We end our journey where we began, on the shore, bathed in moonglow. But now, when we look up, we do so with awareness that the sky is full of moons beyond the one we know, each casting its own orbiting glow, each moving to the gravitational music of its planet. Our Moon's luminous face no longer appears alone. It is an emissary, representing all moons. In its serene light, we can imagine Io's volcanic glow, Europa's icy sheen, Titan's dim sky, and Enceladus's glittering plume. The tide at our toes links to the geysers of Enceladus and the subsurface tides of Europa in the kinship of physics. The gentle night breeze might carry, in our imagination, the faint sulfurous whiff from Io, or the organic tang of Titan's air. We are connected to these distant places through the unity of nature's laws and the journeys of our probes and our dreams.
The hour grows late, the Moon drifts westward, and the sea is calm, nearing low tide. The Earth, Moon, and Sun have aligned just so to create this moment. As we turn to leave the shore, we take one last look at the Moon hanging low, golden and large, and perhaps we whisper a thanks for the tides and the guidance, for the light in darkness, for the stability of seasons, for inspiring us to explore, and for reminding us that even a small world can hold great sway. The Moon and all its sibling moons out there
invite us to keep exploring, to push beyond our home planet and find the wonders awaiting on those many shores. And as the moon's reflection narrows to a glittering ribbon on the ebbing tide, we feel a sense of peace. Above, the sky is sprinkled with stars. Among them, unseen, are countless exoplanets, and surely countless exomoons. We know now that the night is not empty. It is full of other moons circling other skies. Our own moon's glow seems to connect to them, as if weaving a luminous thread through space. In that gentle, eerie light, it's easy to feel that the universe has its rhythms, and moons are a crucial part of that cosmic cadence. The moon gazes down, silent, ancient, and we gaze up, filled with knowledge hard-won, but also with renewed wonder. The scene is almost spiritual, the great quiet orb, the softly heaving sea. One could imagine all the moons of the solar system lined up in the sky in that moment, a string of pearls, each reflecting the distant sun. And us here, a curious species, looking up from the shore of one world, appreciating the existence of many. The story of moons is ultimately a story of relationships, moons and planets tugging on each other, illuminating each other, sometimes destroying each other, sometimes nurturing conditions for life. It's a story that has given our Earth stability and our nights beauty, that has given scientists new frontiers and poets endless metaphors. And it's a story still unfolding, with new discoveries at Jupiter and Saturn, future missions on the horizon, and the first whispers of moons around faraway suns reaching our telescopes. Each chapter deepens our understanding that worlds do not exist in isolation. Gravitational companionship appears to be the rule, not the exception. As you walk away from the shore, the moonlit path on the water broken now into sparkles, you carry with you this awareness. The next time you see the moon high in a twilight sky, or a thin crescent setting at dusk, you might think of the myriad moons circling in the darkness beyond. Io glowing above Jupiter's clouds, Titan's haze under the distant sun, little Dactyl orbiting asteroid Ida, or an unseen exomoon transiting a star far away. Our moon will stand as proxy for all of them, a gentle reminder that in the grand scheme, no world is truly alone. There are always neighbors, partners, companions in the dance. And in that realization lies a profound comfort and excitement. Comfort in knowing our Earth-Moon partnership is a common cosmic theme, and excitement for all the discoveries still awaiting us among the moons of our solar system and beyond. The tide will come in again, drawn by our moon's gravity as reliably as ever, and moonlight will continue to enchant beings on Earth as it has for eons. These simple, timeless phenomena, the moving tide, the shining moon, are echoes of a larger cosmic truth, that worlds tug on each other and light each other in endless cycles. By studying moons, we have uncovered that truth and used it to navigate, to mark time, to pursue scientific insights, and to contemplate our place in the universe. And on a clear night, when the moon is bright, perhaps we can simply let ourselves feel the poetry of it. The same moon that pulls our oceans is, in this moment, also brightening the night, a silent companion to our solitude, just as it is a companion to Earth. In that dual role, gravitational caretaker and silver muse, our moon captures the essence of all moons. They are dynamic actors and serene lights, both physical entities and symbols. Under the calm and intelligent gaze of the moon, we conclude our journey. The ocean's surface lies smooth and reflective now, low tide revealing broad stretches of sand under the lunar glow. The moon will watch over the Earth through this night, as it has since long before humans existed. By the time dawn comes and the moon fades into the blue sky, it will have quietly completed another circuit of its eternal orbit, continuing the tale of moons without end. But we know that story a little better now. We return home, moonlight guiding our steps, minds alive with visions of volcanic moons and icy moons, and all manner of moons circling in the darkness. The night feels just a bit less lonely, and the universe a bit more intimate. We have befriended the moons in our thoughts, and in doing so, forged a connection across the void. Moons. The word now evokes not just the beacon over our planet, but an entire cosmic family of worlds. Fiery, icy, mysterious, and beautiful. And as the moon's reflection finally disappears with the turning tide, we're left with a lasting impression that to study moons is to understand a fundamental part of how the cosmos works and to appreciate the subtle splendors that make our universe so richly textured. In the dance of planets and moons, in the whisper of tides and the glow of moonlight, there is a calm, dreamy poetry, a reminder that even in darkness and silence, there is relationship and light. The story of moons is the story of those relationships, and it's a story we are privileged to witness from our small perch on a moonlit world. It begins with warmth. A gentle golden light caresses your closed eyelids and brushes your skin. You inhale, feeling the soft heat of sunlight that has traveled across empty space to reach you. In this quiet moment, the sunlight feels almost alive, a tender presence on a cool morning. You might take it for granted, this glow on your face, but it is the gift of an immense power. High above, the sun hangs in the sky, pouring out light and warmth in all directions. Now imagine following that warmth back to its source. Drift upwards, leaving the ground behind. The light grows brighter. Blue sky fades to black as you rise beyond Earth's atmosphere, and the sun's true face comes into view. A brilliant star burning in the dark. Here, hovering in space near the sun, there is no air to carry sound, only silence. Yet before you stretches an enormous sphere of glowing plasma, its surface a roiling ocean of fire. Tongues of flame and loops of energy dance at the edges, solar flares arcing outwards, but you hear nothing at all. This close, the sunlight is blinding and the heat is ferocious, but space itself remains eerily still and quiet. Inside the sun's core, countless atoms fuse each second, releasing prodigious energy. Photons born in that deep furnace begin a long random walk outward, bouncing through dense stellar material for ages before finally emerging at the surface as the warm light we know. When they break free, they rush into space at last, racing at light speed. Only about 8 minutes later, some will kiss a human face on a distant blue planet. But here at the source, you float in the glow of creation itself. The sun's surface seethes with granules and magnetic storms, yet from a few million miles away, it looks tranquil. A perfect, bright orb hanging in the void. A crown of wispy solar corona surrounds it, visible as a faint halo. Fine streams of charged particles, the solar wind, flow outward, but you cannot see them. Only feel their faint whisper, if you could hold out a hand. This star, so loud in its nuclear heart, offers its energy to the solar system in utter silence. You turn slowly away from the sun and begin a long spiral journey outward. The light at your back diminishes a little with each passing million miles. Ahead lies the domain of planets, tiny islands of matter circling the parent star. The first island appears very soon. Mercury, the innermost planet, emerges from the glare. Mercury is a little round world of rock and metal, so close to the sun that it's been baked bone dry. As you approach, you see a globe that looks strikingly like Earth's moon, grey, heavily cratered, and airless. Long ago, impacts pockmarked its surface with craters of all sizes, and there have been no winds or rains to soften them. Daylight here is harsh. The sun looms more than 3 times larger than it does in Earth's sky, and the ground under the sunward side blazes under intense heat. You can almost feel it radiating off the cracked regolith. The rocky ground expands and cracks from the scorching temperatures. But Mercury rotates extremely slowly. One day lasts 2/3 of its year. So one side broils in endless daylight, while the other side, long without sun, cools to frigid darkness. In the black sky above the sunlit surface, the stars are visible even at noon, because there is no atmosphere to hide them. If you could stand on Mercury at midday, the sun's fierce light would pour down from a pitch-black heavens. And when night finally falls many Earth days later, it brings a cold more intense than any winter, freezing the ground solid as the heat radiates away into space unimpeded. As you drift low over Mercury's surface, you notice bright streaks around some craters, rays of ejected dust from ancient impacts. You also see great curving cliffs, hundreds of miles long, that cut across craters and plains. These scarps formed as Mercury's interior cooled and shrank, wrinkling the surface like a dried apple. Mercury is astonishingly dense for its size. Deep below, it holds an outsized iron heart, a metal core taking up most of the planet's volume. That heavy core and the sun's gravitational grip keep Mercury locked in a strange dance. It spins 3 times for every 2 orbits around the sun. In Mercury's polar recesses, where the sun's rays never quite reach, there are deposits of water ice hidden in eternal shadow inside craters. It seems impossible, yet even at the sun's doorstep, frost can exist in the dark. Mercury is a world of extremes: blazing day, airless night, searing sun, and hidden ice. It is the innermost sentinel of the sun, a little cratered enigma racing around the star every 88 days. You leave Mercury behind, a tiny scorched globe receding into the brilliance, and journey outward to the next planet. As the sun's glare lessens a bit more, a pale yellow-white beacon appears ahead: Venus. From a distance, Venus is breathtaking, a perfect pearl of a planet, swathed in thick white clouds that reflect sunlight brilliantly. It outshines everything in the night sky, but the moon, a lovely evening star. Yet that beauty hides a deadly secret. Dropping down toward Venus, you penetrate its cloud layer and enter a smothering world of golden twilight. The atmosphere here is a dense broth of carbon dioxide with clouds of caustic sulfuric acid droplets. The further you descend, the darker and more orange the light becomes, tinted by the thick haze. Venus's clouds form an ever-present global blanket, so the surface knows nothing of stars or blue sky. Only a dim, diffuse illumination under eternal overcast. Deeper and deeper you go, and the pressure mounts. At the surface, the atmosphere presses down at 90 times the pressure of Earth's, like being 900 meters under the ocean. The air is a supercritical fluid, almost syrupy in its density. Here, a human would be crushed instantly. And the heat is astonishing. The temperature near the ground is hot enough to melt lead and zinc. The rocks themselves glow faintly dull red from the furnace-like environment. There is no water. Any that Venus once had boiled away eons ago in a runaway greenhouse inferno. In the dim light, you make out a barren landscape. Rolling plains of volcanic rock. Sharp-edged stones under an orange sky. The terrain is strangely quiet and still. No rain ever falls. No wind stirs at ground level. The air is too heavy. Only far above, at the cloud tops, do high winds race around the planet, shrouding it in fast-moving storms that never touch the hellish ground below. Volcanoes dot the surface, some enormous shield volcanoes bigger than any on Earth. Much of Venus appears to be covered in vast basaltic plains from ancient eruptions. In some places you see fields of strange domes and arachnoid patterns, volcanic landforms crushed and contorted by the intense pressures. The ground shows evidence of past lava flows and perhaps current volcanism, fresh-looking basalt, and signs that the planet may still be geologically alive. But if volcanoes erupt here, they do so in utter secrecy beneath the perpetual cloud deck, their red glow absorbed by the choking haze.
The heat on Venus is unrelenting and nearly uniform across the planet, day or night. Venus turns so slowly on its axis, it takes longer to rotate once than to orbit the Sun, that a single Venusian day lasts almost 4 Earth months. But the thick atmosphere evens out the temperatures, carrying warmth to the night side. It is a world in slow motion, skies forever darkened by cloud, surface baking in constant dusk. For billions of years, Venus has known no relief from this self-made purgatory. Long ago, perhaps, it might have had shallow seas and milder air before something went terribly wrong. Now it stands as Earth's twisted sister, nearly the same size and composition as our home, yet completely inhospitable, a vision of a greenhouse nightmare. The only hints of anything gentle are far above, about 50 kilometers up. In the upper cloud layers, the temperature and pressure are nearly Earth-like. High in those clouds, strange streaks and patterns have been observed, perhaps just chemistry and droplets. But some have speculated about airborne microbial life surviving in the temperate heights, living in acid droplet clouds. It remains only a tantalizing idea. Leaving Venus, you ascend back through thick orange clouds that thin to bright white and finally break into clear space above. The planet's shining veil closes beneath you, hiding that toxic surface once more. You are glad to leave the crushing pressure and stinging acid behind. Out here above the clouds, Venus looks serene again. It is hard to imagine the inferno lurking below that placid cover. With a silent farewell to the morning star, you journey onward. The sunlight now is gentler, more golden, as you approach the orbit of Earth. Soon, a jewel appears in the blackness, a blue marble adorned with swirls of white. Our home, Earth, reveals itself in full sunlit glory, a sight to fill the heart with wonder. From space, Earth is a vision of vibrant color, deep sapphire oceans, bright tan deserts, verdant green-brown landmasses, and above them, swirling white cloud formations. A delicate film of atmosphere encircles the planet as a thin, glowing blue rim at the horizon. Compared to the harsh, airless moon or the choking blanket of Venus, Earth's atmosphere is a tender and life-sustaining mix, just thick enough to spread warmth and allow weather, transparent enough to let sunlight nurture the surface below. You descend toward the Earth, and as you slip into the atmosphere, you feel the first tug of aerodynamics, hear the faint whistle of wind. Thin, high air grows to a breathable breeze. Puffy white clouds drift below, casting soft shadows on the oceans. You pass through a layer of wispy cirrus and emerge over a vast expanse of ocean. Sunlight dances on waves that roll and break in white foam. The air is sweet and carries the scent of salt and living things. Seabirds wheel and cry beneath you as you skim just above the waters. Unlike any other planet in our solar system, Earth's surface is mostly liquid, an ocean world where life began in warm primordial seas. The blue expanse seems endless and calming. Moving over a coastline, you see green forests hugging the shores and brown mountains further inland, capped with snow. Rivers sparkle in the sunlight, winding from highlands down to estuaries, carving valleys over eons. In the forests and plains, every patch of Earth is alive, a tapestry of life forms in every shape, each contributing to the grand harmony of the biosphere. You sense activity and energy everywhere, the flutter of leaves in the breeze, the chirp of insects, the distant roar of a waterfall, perhaps even the murmur of human civilization if you listen closely. Faint hints of voices or engines far below, nearly lost in the vastness. Earth is alive both geologically and biologically. Its crust continually renews itself through plate tectonics. Continents drift imperceptibly, colliding to thrust up mountain ranges and pulling apart to create new ocean floor. Volcanoes occasionally pierce the surface, bringing up nutrients from Earth's depths, and earthquakes remind us that our planet's skin is restless. And Earth is alive in another sense. It hosts a biosphere that has transformed the air and land.
green plants inhale carbon dioxide and exhale oxygen, animals do the opposite. Life and Earth dance together, each shaping the other. The atmosphere you breathe, rich in oxygen and balanced with nitrogen, exists only because countless tiny organisms in the ancient seas produced oxygen as a waste gas over billions of years. Now forests and phytoplankton maintain that balance. The result is air that allows both intense activity and gentle breezes, clouds and rain, climate and seasons. Earth sits at just the right distance from the sun, not too hot, not too cold, allowing water to remain liquid at the surface, cycling perpetually from ocean to cloud, to rain to river, and back to ocean. This endless water cycle weaves weather and nourishes life. On the day side, puffy white clouds gather over tropical seas, releasing afternoon showers. In the night, thunderstorms flicker over equatorial lands, illuminating clouds from within with lightning's glow. Polar auroras shimmer occasionally at the highest latitudes, painting the sky with silent curtains of green and red light when solar particles strike Earth's magnetic field. High above, Earth's magnetic field forms an invisible shield, deflecting dangerous charged particles from the sun, ensuring the surface is not stripped of its atmosphere or sterilized by radiation. This magnetosphere funnels some particles to the poles, where they create those auroras, a gentle, beautiful side effect of our planet's protective embrace. Circling the Earth is its constant companion, the Moon. As you move around to Earth's night side, lit now only by starlight and the silver glow of the Moon, you gaze up from an earthly hillside at the lunar disk. The Moon hangs in the sky, airless and silent, shining by reflected sunlight. This grey orb has been a beacon for humans for as long as we have existed, its phases marking the passage of months, its gravitational pull quietly stirring our ocean tides. You decide to visit our Moon, rising off the Earth's surface once more and gliding toward that familiar cratered globe. In hours you arrive, settling down onto a vast lunar plain. The scene is otherworldly. The ground is covered in fine charcoal-colored dust, undisturbed save for ancient meteorite craters and, in certain spots, the faint tracks left by human explorers. Here on the Moon, the sky is pure black even when the sun is up. The harsh sunlight casts inky shadows among the rocks. You notice footprints pressed into the powdery soil, footprints left by Apollo astronauts half a century ago. They look as fresh as if made this morning. With no atmosphere here, there is no wind or rain to ever erase them. They could remain for millions of years, silent testimony to humanity's reach. The Moon's landscape is starkly beautiful in its simplicity. Rolling plains of solidified lava called Maria, lighter highlands densely cratered by impacts, and the pitch-black shadows inside deep craters near the poles where sunlight never shines. In some of those craters, scientists have discovered ice mixed with the soil, delivered by comets and preserved in the perpetual cold of shadow. You gaze back toward Earth, a blue marble now rising above the Moon's horizon. The Earth is many times larger in the lunar sky than the Moon is in Earth's sky, and it hangs almost motionless because the Moon keeps one face always turned toward us. A dazzling halo of blue and white, our home planet looks alive and fragile from here, suspended in space, half illuminated. It casts a gentle pale glow across the lunar ground. Earthshine, lighting the night portions of the Moon, just as moonlight illuminates Earth's night. The connection between Earth and its Moon is profound, gravitationally locked in an ancient dance, each affecting the other. The Moon's pull raises the ocean tides on Earth, and perhaps helped stabilize Earth's tilt over geological time, smoothing the seasons. And Earth's gravity, in turn, raised enormous tidal stresses in the young Moon that may have shaped its early volcanism. Climbing back into space, you leave the moon's silent regolith and continue outward. You have now passed the sun's first two inner worlds and Earth with its satellite. Next in line is Mars, the red planet, glowing with a rusty hue in the distance. Approaching Mars, you find it smaller than Earth, about half the diameter, and wrapped in a much thinner atmosphere. Its ruddy color comes from iron oxide, essentially rust, in the dust that covers its surface. Once you enter the Martian atmosphere, you realize how tenuous it is. Just a faint whisper of carbon dioxide gas, less than 1% the density of Earth's air. The sky here has a butterscotch tint, tinted by fine dust suspended high above. In the daytime, the sun is a bit dimmer and smaller than on Earth, its warmth far weaker in the thin air. You drift down to the surface near the Martian equator, landing on a broad reddish plain strewn with rocks. The ground is covered in reddish sand and dust that clings electrostatically to everything. In the far distance, a colossal mountain rises. Olympus Mons, the largest volcano in the solar system. Its huge bulk so wide and gentle sloped that from here you might not realize you're looking at a mountain at all, but it towers many kilometers above the surrounding plains. In another direction, you see a great canyon system cutting across the landscape, Valles Marineris, a chasm that would span from Los Angeles to New York if it were on Earth, and several times deeper than the Grand Canyon. It rends the Martian crust with steep cliffs and layered walls, colored ochre, gold, and red. This immense scar speaks of tectonic forces or something that nearly tore the planet apart long ago. The air is deathly still. Occasionally a light breeze may stir some dust, but Mars's atmosphere is usually eerily calm. Yet at times it can erupt. Global dust storms have been known to engulf the entire planet, turning the sky a tawny brown for months. But on this day, it is tranquil. The temperature is cool, near freezing at noon, but will plunge far below freezing after sunset. Overhead, the sky is a yellowish brown near the sun, fading to a deeper blue-gray at zenith. There are wispy clouds of ice occasionally, and in the late afternoon, you might even see a delicate streak of cloud catching the sun. Mars is a desert world, cold and dry. But as you wander, evidence of water is all around you in the shapes of the land. You float over an ancient river valley, now completely dry, its once sinuous channel carved into the rock. Long ago, water, actual liquid water, flowed here, possibly in rivers and lakes. You spot what looks like an old delta where a river met a basin, the telltale fan shape of sediment. And that great canyon, Valles Marineris, may have been enlarged by water flowing out from underground. Today, however, Mars is a freeze-dried world. The only water you see lies locked up as ice. Caps of bright white at the poles gleam against the rusty terrain, composed of water ice and carbon dioxide ice, dry ice, that grows and shrinks with the seasons. Just beneath the surface at these latitudes, a permafrost of ice extends for miles. The sun is setting now on Mars. In the west, the sun descends as a small bright disk, and the sky around it turns coppery. Curiously, just as the sun drops below the horizon, the sky directly above the setting sun glows a cool bluish tint for a few moments, a quirk of how the fine dust particles scatter blue light more efficiently when the light path is long. Twilight on Mars is blue. Soon, the first stars prick through the sky, and an intense cold permeates the thin air. In the darkness, you notice two tiny moons rising. Phobos, the larger, is a misshapen rock only about 22 kilometers across, looking more like a big asteroid than a proper spherical moon. It orbits Mars with dizzying speed, crossing the sky from west to east in just 5.5 hours. Deimos, smaller and farther, appears as a star-like point of light. These moons are likely captured asteroids, pilfered by Mars's gravity long ago. Phobos hangs so close that in some regions of Mars, it would appear to dart overhead multiple times each day. Its surface is dark grey and heavily cratered. A large crater named Stickney gives it a somewhat skull-like appearance. Someday Phobos will spiral inward and break apart or crash into Mars. But for now, the two potato-shaped moons silently circle their rust-colored master, witnessing the red planet's lonely desert sunsets. Mars feels like a world on the cusp, a once active planet, now largely asleep. Long ago, it had volcanoes that built towering mountains and water that carved channels through its soil. Something changed. The volcanoes grew quiet, the water froze or escaped, and the atmosphere thinned to nearly nothing. Now it waits, an enormous and silent desert, tinted red by the oxidized dust of ages. Still, it beckons us with its similarities to our own world: polar caps, day lengths and tilted axis that give it seasons like Earth's, though colder, and a geology that speaks of processes familiar yet extinct. In its soil and rocks, perhaps microbial life once took hold in the wetter past. Perhaps even now some hardy remnants survive hidden beneath ground, clinging to warmth and moisture. Mars keeps its secrets for now, whispering them in dry winds that occasionally skip dust devils across the plains, dancing columns of dust that briefly snake upward before dissipating. You watch one of these dust devils swirl in the distance, tracing a delicate path and leaving dark streaks where it cleared the reddish dust off the surface below. Then it's gone, and stillness returns. You have now traveled roughly half the length of the solar system's planetary zone. Ahead lies the vast expanse beyond the inner rocky worlds, a domain of giants and mysteries. As you depart Mars, you traverse the boundary between the inner and outer solar system. The sun is smaller now behind you, though still bright. Moving outward, you enter a wide region populated not by singular planets, but by countless smaller bodies, the asteroid belt. This torus of debris stretches between Mars and Jupiter, filled with remnants from the solar system's formation. Contrary to Hollywood depictions, the asteroid belt is mostly empty space. The asteroids within are separated by hundreds of thousands or even millions of kilometers. You could drift through and likely never encounter one unless you deliberately navigated to it. But imagine you could see all these rocks at once, speed up time, or put them all before you. You'd behold a vast swarm of ancient mountain-sized boulders and smaller rocks, each tumbling in the sunlight, casting stark shadows on themselves. Some are solid metal, shiny nickel-iron fragments of long-destroyed protoplanets' cores. Others are porous rubble piles of rock and dust, only lightly held together by gravity. Most are irregular, cratered from countless collisions with their brethren. These are the leftovers that never formed a planet, perhaps due to the disruptive gravity of nearby Jupiter. You pass one of the largest asteroids, Ceres, a dwarf planet roughly 950 kilometers wide. From a distance, it looks almost spherical, a dull grey world with bright salty white patches gleaming within some craters. Those bright spots mark places where briny water or slush oozed up from Ceres's interior and deposited reflective salts upon evaporating, evidence that even this small body has or had a subsurface ocean, or at least pockets of liquid in its past. Ceres is a gentle world with a light gravity. Long ago, it may have been warm enough inside to differentiate into layers. Today it's cold, but still may hide slushy mud or ice deep down. As you glide low over one bright crater named Oort, you see the ghostly shimmer of those salt deposits, remnants of cryovolcanism that happened within the last few million years, nearly yesterday on geological timescales. Ceres, quiet now, hints at activity not so very long ago. Farther on, you pass by an oddly angular rock. It's Vesta, another giant asteroid, with a huge gouge at its south pole from a titanic impact. That impact blasted out enormous quantities of debris. In fact, many meteorites that fall on Earth are pieces of Vesta, identified by their unique mineral signature. Vesta's surface is a patchwork of light and dark areas, ancient basaltic lava plains and brighter highlands. It almost became a planet. It has a core and mantle like one,
but it never grew quite large enough.
Scattered through the asteroid belt are countless smaller bodies, like little Ida with its tiny moon dactyl or metallic Psyche, shining faintly as it tumbles end over end. Occasionally, two asteroids have collided and shattered, and you see their fragments following similar orbits, family groupings of rubble slowly dispersing over eons. In this region, the echoes of creation and destruction linger on every scarred surface. It's serene now, but the belt's history is violent. The asteroids we see are the survivors of an early era of frequent collisions. Even today, once in a while, asteroids still collide, and the impact sends out showers of debris. Some of that debris might eventually wander inward as meteoroids and sometimes reach Earth, flaring as shooting stars or meteorites on the ground.
Coasting outward through the asteroid belt, the sun continues to shrink behind you. The inner planets are now tiny dots lost in a brilliant solar glare. Ahead, an entirely different kind of planet awaits, the first of the gas giants. Jupiter grows from a star-like point to a visibly disk, then to an immense striped globe dominating your field of view. You have arrived at the king of planets. Jupiter is staggering in its size. Over 11 Earths could be lined up across its face. As you come alongside it, you feel dwarfing humility before this banded colossus. Its upper atmosphere is patterned with broad bands of white, ochre, and reddish-brown wrapping around the planet. These are rows of clouds driven by powerful winds that roar east-west at hundreds of kilometers per hour in opposite directions for adjacent bands. The lighter bands, called zones, are higher clouds of ammonia ice, while the darker belts are deeper layers where other chemicals give ruddy and yellow hues. The boundaries between belts and zones are turbulent, with eddies and swirls where the opposing winds shear against each other. One feature stands out especially on Jupiter's canvas: the Great Red Spot, a titanic storm twice as wide as Earth. This oval tempest has been churning in Jupiter's southern hemisphere for at least 350 years, since humans first observed it through telescopes, and likely far longer. Within its brick red oval, winds howl counterclockwise around a high-pressure center, and ammonia clouds pile high. It is a cyclone of enormous proportions, its outer edges flaked by smaller vortices. As you hover above it, you see the spot's color has softened to a coral or peach tone nowadays, and it has shrunk somewhat compared to historical records. But it is still a vast, persistent hurricane beyond any earthly scale. We could drop our whole planet into it with room to spare. Lightning crackles elsewhere on Jupiter too. Near the poles, bright white thunderstorms erupt from deep water cloud layers, occasionally illuminating the cloud tops with brief flashes. Jupiter's atmosphere is dynamic and alive with activity, a ceaselessly roiling artwork of fluid physics. There is no solid ground for you to land on here. Jupiter is likely composed mostly of hydrogen and helium gas, with increasing pressure and density as you go down. If you descended through those clouds, the atmosphere would thicken into a hot soup, eventually into a fluid state, and deeper still perhaps into metallic hydrogen that conducts electricity like a metal. Far below that, somewhere in the crushing depths, may lie a dense core of rock and ice perhaps, but no human-made probe could survive long enough to reach it. Instead, you remain high in the atmosphere, skimming along the cloud tops at a safe distance. The view is magnificent. It's like floating above an unending cloud ocean, with rolling formations and whirls the size of continents. Long, snaking cloud bands trail around, and small oval storms, white or brown, dot the belts, each one a cyclone or anticyclone. High-altitude haze in places casts shadows on lower cloud decks. Over the poles, which were unseen by any human until recently, you would find swirling clusters of cyclones arranged in geometric patterns. Immense polar vortices, with unexpected symmetry, quietly rotating in the dim sunlight at high latitude. Jupiter is more than just a planet. It's almost a miniature solar system of its own. Circling around it are dozens upon dozens of moons.
a retinue of diverse worlds bound by Jupiter's mighty gravity. 4 of those moons are so large and intriguing that they draw nearly as much interest as the planet itself. If you drift outward a bit to a vantage where you can see Jupiter's entire system, the 4 Galilean moons line up like tiny disks orbiting in the plane of Jupiter's equator. Innermost is Io, a moon about the size of our moon, but painted in vivid mottled yellows, oranges, and black. Io is the most volcanically active body in the solar system. As you approach Io, you notice strange blotches and sulfurous colors on its surface. Those are volcano calderas and deposits of sulfur compounds. Suddenly, on the terminator, the line between day and night, you catch sight of a towering plume, a volcanic eruption in progress. A fountain of sulfur dioxide gas and dust is blasting out of Io's surface, arcing high into space to an altitude of several hundred kilometers before the frost of space causes it to snow back down. Io's gravity is low, so these plumes form umbrella-like canopies, like giant blooming flowers of smoke. The moon's entire surface is constantly repaved by lava flows. Lakes of molten sulfur glow red in the dark, and fresh lava plains cool to dark crusts. Io's intense volcanism is powered by Jupiter's relentless tidal grip. The giant planet's gravity flexes Io's interior as the moon orbits, generating heat by friction and melting Io's insides. No impact craters are visible on Io. Any that form are quickly buried under new volcanic deposits. The air is extremely thin, just a wisp of sulfur dioxide, but enough to freeze at night and form a faint transient atmosphere by day. Io is a tortured world of fire and brimstone, literally a moon on fire under Jupiter's gaze. Next out is Europa, only slightly smaller than our moon. Europa's surface is strikingly smooth and bright, crisscrossed by long reddish-brown streaks like cracks on an eggshell. That analogy isn't far off. Europa is encased in a shell of water ice, perhaps 20 kilometers thick, and beneath that ice lies a global ocean of liquid water. It's hard to believe at first. You stand on a world so cold that ice is rock, yet beneath your feet is likely a deep saltwater sea kept liquid by tidal heating from Jupiter's pull. Europa's surface tells a tale of this hidden ocean. The network of streaks and cracks suggests that the ice crust is continually fractured and shifted by tides, and occasionally water or slush wells up through the cracks to resurface the moon. Hardly any craters mar Europa's surface, implying it is young and continuously renewed. At a few spots, you see what might be small plumes, geysers of water vapor, venting into space through fissures in the ice, evidence that sometimes the ocean below can communicate with the vacuum above. The sunlight here is weak, and the surface is bitterly cold, around 160 degrees Celsius. But the ocean below, sealed under the ice, might be a comfortable temperature, and likely completely dark, except perhaps for faint glow from any hydrothermal vents on the ocean floor. Yes, deep down, at Europa's rocky core ocean interface, tidal heating may drive undersea volcanoes or hot springs, providing chemical energy and warmth. It is tantalizing to imagine life there in the deep, perhaps simple microbes, maybe even complex organisms, living out of view in the black waters of an alien ocean. You run a hand over the ice. It's hard as granite at this temperature. Reddish-brown stains near cracks hint at salts or organic compounds brought up from below. Europa is silent, but it holds its secrets close. An ocean under ice, a possible cradle for life adrift in Jupiter's powerful embrace. Beyond Europa orbits Ganymede, largest of the moons. In fact, the largest moon in the entire solar system, even bigger than Mercury. Ganymede appears as a mottled grey-brown sphere with regions of dark ancient terrain and lighter, somewhat younger, grooved regions. It has clearly suffered countless impacts. Its dark areas are saturated with craters. But in the lighter areas, you see long parallel grooves, signs of past tectonic activity that somehow stretched and broke the crust. perhaps from internal upwellings or global expansion. Ganymede is a world of water ice and rock. Its surface is mostly ice, as hard as rock, peppered with craters whose ejecta splashed out bright rays of fresh ice. Like Europa, Ganymede too is believed to hide a subsurface ocean, though deeper below, a thicker crust of ice. And remarkably, Ganymede has its own magnetic field, the only moon known to have one, indicating it likely has a molten iron or iron sulfide core, creating a dynamo like Earth's. As you pass through Ganymede's vicinity, you might feel a slight tug and wobble in Jupiter's magnetic field, evidence of Ganymede's magnetic bubble embedded within the giant planet's magnetosphere. On Ganymede's surface, if you stood there, Jupiter would loom huge in the sky, many dozens of times larger in apparent size than our moon looks from Earth. Its banded face would be visible if the side of Ganymede you're on is facing Jupiter, perhaps with the great red spot discernible as a reddish oval. The sunlight here, 5 times weaker than at Earth, still provides ample daylight on the ice. At night, the sky is dark and full of stars, and Jupiter would be an awesome, softly glowing presence, lighting Ganymede's ground in a dim twilight whenever it hangs above the horizon. Farther out lies Callisto, the most distant of the Galilean moons. Callisto is a world that appears ancient, almost primordial, with a densely cratered crust of ice and rock that seems never to have been reworked by internal forces. Its entire surface is covered in overlapping craters upon craters, so densely packed that new impacts must obliterate old ones. The largest impact basins have concentric rings like ripples frozen in time, Valhalla and Asgard, enormous bullseye patterns from titanic collisions in the far past. Callisto's surface glints with countless tiny bright spots against a darker background. The bright spots are relatively fresh ice exposed by impacts, contrasting with the darker, dustier surrounding terrain that has been weathered by eons of micrometeorite bombardment and radiation from Jupiter. Beneath Callisto's heavily cratered crust, there may also lurk a hidden ocean, according to magnetic data from spacecraft. Even this seemingly inert moon might hold a liquid water layer deep below, sandwiched between ice layers. If so, it is likely heavily mixed with salts and ammonia, and perhaps it never interacts with the surface. Callisto does not exhibit signs of geological activity. It appears to be a relic from the early solar system, its face virtually unchanged for 4 billion years. Drifting above Callisto, you reflect that this moon is like a museum piece, preserving the record of the heavy bombardment epoch in the solar system's youth, unlike its sibling moons which have erased or repainted their surfaces through internal activity. Leaving Callisto, you have sampled the 4 great moons of Jupiter: fire, ice, and 2 shades of twilight between, each distinct, each fascinating. But Jupiter has many more smaller moons too, tiny irregular captured asteroids far out and closer in, a retinue of small inner moons shepherding a thin system of rings. Yes, Jupiter has rings as well, faint, dusty rings, discovered only when spacecraft flew behind the planet and saw sunlight forward scattered. These rings are not like Saturn's broad icy ones. Jupiter's are subtle, made of micrometer dust grains slowly spiraling inward. The dust likely comes from meteoroid impacts on the inner moons like Amalthea and Thebe, each impact kicking up debris that then orbits as a tenuous ring. You might not notice Jupiter's rings unless you catch them at just the right angle with the sun. Still, they form a gentle band of light hugging the planet's equator, a whisper of structure around the gas giant. Turning away from Jupiter, you venture onward. The sunlight now is much fainter than when you began, only a quarter of its intensity at Earth's orbit. Stars crowd the sky as the ambient glare of the sun lessens, but ahead, another jewel awaits: Saturn, Lord of the Rings. Even from afar, Saturn captivates. Its pale golden globe is encircled by a magnificent system of bright, shining rings that span hundreds of thousands of kilometers. As you approach, the rings resolve into countless individual slabs of ice and rock, all orbiting in a flat plane like a celestial vinyl record. Saturn itself is a gas giant slightly smaller than Jupiter, with a more delicate hue. Bands of butterscotch, cream, and grey slide gently around its atmosphere. Its features are more muted than Jupiter's violent contrasts. But Saturn too has storm systems and high-speed winds. A broad, hazy belt girds its equator, and near its north pole you find a strange geometric wonder, the famous hexagon. It is a six-sided pattern in the cloud tops at the pole, perhaps caused by the peculiar dynamics of a standing wave in the atmosphere. At Saturn's center, unseen below the clouds, lies a smaller core of heavy elements. But like Jupiter, Saturn has no solid surface at its cloud tops, just a gradual transition from gas to fluid. Saturn is less dense than water. In theory, if you had a bathtub big enough, Saturn would float. Yet it is the rings that draw your eye above all. You glide just above the ring plane, skimming the outer edge of the main rings. Stretched out below you is an almost flat expanse of icy particles. Some are grains of dust, others boulders the size of a house. They shine brilliantly in the sun, like countless diamonds on black velvet. The rings are astonishingly thin, in places only tens of meters thick, essentially two-dimensional when seen edge-on, though tens of thousands of kilometers in radial extent. Gently, you dip down into a gap between ring sections. Around you, ice chunks tumble slowly. If you were very quiet, you might even hear the tinkling of tiny impacts as particles collide softly or clump together briefly. Saturn's rings are mostly pure water ice, which is why they gleam so brightly. They likely formed from the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Now these countless fragments spread out in their orbits, sculpted by gravity into several distinct ring zones, divided by thin gaps. Some gaps, like the Cassini division, are maintained by the gravitational influence of Saturn's moons. Small shepherd moons like Pan and Daphnis carve narrow channels, their gravity herding ring particles and creating sharp edges and waves in the rings. Looking down at Saturn's rings from above is one of the most sublime views in the solar system. You see delicate spiraling density waves, like ripples or grooves in a vinyl record, caused by orbital resonances with moons further out. You see subtle color differences. The B ring is brilliant white, the C ring more dusky and translucent. Sometimes you see fleeting spokes, ghostly radial features that appear and dissipate, perhaps caused by electromagnetic effects, levitating fine particles temporarily above the ring plane. The rings cast a broad shadow on Saturn's cloud tops, a series of dark bands across the planet's face. Conversely, on the night side of Saturn, the rings reflect sunlight and cast a soft illumination, so that Saturn's night side is never completely dark when the rings are in sunlight. Yet for all their glory, Saturn's rings are transient on geological timescales. Already, ring material is slowly raining down onto Saturn, pulled by gravity and dragged by magnetic fields. It's estimated that in another 100 million years or so, the main rings may become thin and eventually vanish, either accreted onto Saturn or dispersed into space. We are lucky to live in an epoch when Saturn wears such magnificent rings. They may be a relatively recent adornment, and one day they will dissipate. But in this moment, as you float among them, they appear timeless and serene, a cosmic masterpiece of natural sculpture. Emerging from the rings, you turn attention to Saturn's family of moons. At least 82 moons circle Saturn, and more continue to be discovered. They range from tiny, irregular chunks a kilometer across to the giant Triton, second largest moon in the solar system. Each moon has its own character. Let us visit a few of the notable ones. First and foremost is Triton. As you approach Triton, you see a hazy orange globe, the only moon in the solar system with a substantial atmosphere. In fact, Triton's atmosphere is thicker than Earth's, made mostly of nitrogen with a touch of methane. It completely hides the surface from visible sight. You descend through this thick orange air, and at around 50 kilometers up, you pass through a layer of methane clouds. A gentle rain of liquid methane might be falling from some of these clouds, not water, which is frozen as hard rock on Titan, but methane, which at Titan's frigid 180 degrees temperature can exist as a liquid. Breaking through the cloud deck, you reach the surface and settle gently onto an open plain near a lake. Yes, Titan has lakes, not of water, but of liquid hydrocarbons. Before you, stretching to the horizon, is a mirror-like expanse of liquid methane and ethane, something like a primordial earthly lake, but under an alien starless sky. The sun here is a feeble yellow point, smothered in haze, so it's a dim twilight at noon. Across the liquid surface, you see the reflection of Saturn's distant glow in the hazy sky above, though if Saturn is above the horizon, it would only appear as a pale light smudge due to Titan's thick atmosphere. Walking on Titan would be strangely pleasant in some ways. The thick atmosphere and low gravity give it a surface pressure similar to Earth's, and gravity only 1/7 of Earth's. You could actually strap on wings and fly in the dense air if you ran and flapped hard enough. But the temperature is unimaginably cold to us, and you'd need a heated suit to survive, not to mention an oxygen supply. The landscape around you on Titan might look surprisingly familiar in form. You see what appear to be river channels carved into the icy ground, leading to this lake, indeed named Kraken Mare. Rounded pebbles of water ice and solid hydrocarbons lie at your feet, smoothed by flowing liquid. There are even gentle waves on the lake's surface when the wind picks up. At the shore, a sludge of organic rich mud, a bit like wet sand made of plastic, squelches underfoot. Titan's atmosphere, laden with smoggy hydrocarbons created by sunlight-driven chemistry high above, deposits a constant drizzle of complex organics onto the surface. Over millions of years, Titan's surface has accumulated a wealth of carbon-rich compounds, the building blocks of possible biology, waiting perhaps for a spark of life. The air has a hint of aroma if you could smell it through a filter, perhaps a tang of hydrocarbons, akin to gasoline mixed with fainter, sweeter notes from other organics. Titan's world is like a deep-freeze laboratory of prebiotic chemistry, possibly reminiscent of early Earth's chemistry, but at cryogenic temperatures and without liquid water. Mountains of rigid water ice, hard as rock, rise in the distance, softly rounded by the thick atmosphere's lack of erosive power beyond the occasional methane rain. A low sun hangs in the perpetual haze. Daytime is a dusky affair, and as night falls, the clouds and haze block any stars. But occasionally, if the sky clears enough or in certain infrared transparency windows, the majestic presence of Saturn might faintly appear, huge and ghostly, occupying a broad region of Titan's sky, a pale source of light far more subdued than our moonlight back on Earth. Lightning is rare on Titan, as the atmosphere lacks strong convection generally, but who knows? Perhaps a rare thunderstorm could flicker in the distance over one of the hydrocarbon seas, briefly illuminating the alien shoreline. Titan quietly reminds us of Earth in mirror form, an active cycle of liquids, but made of methane. A thick atmosphere, weather, lakes, rivers, maybe even cryovolcanoes that erupt cold mixtures of water and ammonia from Titan's interior. It is a dynamic and complex world, all its own, one that could perhaps harbor very strange life that uses liquid methane instead of water. If such life exists, it would metabolize and move in extreme slow motion due to the cold, but it would find Titan a comfortable home. Next, you bid Titan farewell and venture to tiny Enceladus, another of Saturn's remarkable moons. Enceladus is tiny, only about 500 kilometers across, but brilliantly bright. Its surface is fresh, clean ice reflecting almost all the sunlight. As you orbit over Enceladus's southern hemisphere, you witness a breathtaking sight. Multiple geysers of fine icy mist spraying out from long tiger-stripe fissures near the South Pole.
Enceladus is literally a cosmic fountain. These plumes are composed of water vapor and microscopic ice particles being vented from its interior ocean out into space. The jets feed a large diffuse ring around Saturn, the E-ring, with their ejected material. You fly through a plume, it's unavoidable, as they shoot hundreds of kilometers up. For a brief moment, your spacecraft's windows accumulate a fine frosting as the water vapor hits and freezes. Sampling the vapor would reveal salty water with organic compounds, essentially bits of the subterranean sea of Enceladus. Beneath the surface of this small moon lies a liquid water ocean sandwiched between the rocky core and icy crust, kept warm by tidal flexing from Saturn and perhaps radioactive decay. The plumes erupt through cracks in the ice, likely on the ocean floor. Hydrothermal vents add heat and minerals to the water, which then travels upward and escapes at the cracks. You descend towards one of those long fissures, known as Damascus sulcus, and peer into a bluish trench from which a mist continually emanates. At the edges of the trench, the ground is stained with deposited frost and possibly simple organics from the ocean spray. Surrounding terrain is relatively young, few craters, and marked by curving fractures and ridges. Enceladus's environment is like a natural spa of the solar system. Under its ice, warm water and perhaps life-sustaining chemicals brew and belch out gracefully into space. This moon, tiny as it is, has become one of the prime targets in the search for extraterrestrial life. One can imagine organisms around those hypothesized hydrothermal vents in Enceladus's ocean, feeding on mineral-rich fluids, living in total darkness, but thriving in warmth provided by Saturn's tidal energy. As in Europa's case, we have yet to confirm life, but all ingredients are there. Even in deep space far from the sun, life might find havens where energy and liquid water exist.
Enceladus orbits within Saturn's faint E-ring, which it maintains. When sunlight streams through the E-ring at just the right angle, you see a diffuse glitter around Saturn, billions of tiny ice grains catching the light. Some of those grains will eventually fall back onto Enceladus's surface like fresh snow, keeping it bright. Others escape Saturn's gravity or fall into Saturn eventually. In effect, Enceladus is a little icy comet continuously active around Saturn. Another notable moon is Iapetus, which you visit next on your Saturnian tour. Iapetus is half bright ice, half dark as coal. As you approach, you notice its striking two-tone appearance. One hemisphere, the leading face of its orbit, is coated in dark material, making it look like a yin-yang symbol. The other trailing side is bright white ice. Iapetus also has a bizarre equatorial ridge running most of the way around the moon's center, like a walnut seam, making it resemble a piece of a giant shell. This ridge is up to 13 kilometers high in places. No one knows exactly how it formed, perhaps long ago rapid rotation or a collapsed ring that settled on the surface. You pass over a region known as Cassini Regio, the dark hemisphere, and the ground below looks like asphalt sprinkled with frost. Craters on the dark side have bright rime along their rims, where lighter subsurface ice was exposed by impacts. It is a world of stark contrast, quietly circling Saturn at great distance, far beyond Titan. The dark coating is likely a thin layer of organic rich dust, perhaps swept up from outer irregular moons or from Phoebe, an outer moon of Saturn, and deposited on Iapetus's leading face like bugs on a windshield. This deposited material warmed slightly in sunlight and sank into the ice, creating a runaway effect of sublimating the bright ice and leaving behind more dark stuff, thus darkening that side further. Meanwhile, water vapor redeposited on the colder trailing side, making it even brighter. Thus, Iapetus became an extreme study in albedo dichotomy. Time would fail to speak of all Saturn's moons. The tumbling Hyperion, shaped like a sponge, chaotic in its spin, or tiny Mimas, with its huge crater resembling the Death Star, or Enceladus's siblings Tethys, Dione, and Rhea. each with its own pattern of cracks or craters, or ancient rings of frozen impact basins. Saturn's system is a rich archipelago of worlds, each worthy of exploration. But the cosmic clock urges you onward to the next realm beyond Saturn. Past Saturn, the sunlight dims further. The warmth of the inner solar system is far behind. Now you enter the domain of ice giants. First comes Uranus, a pale cyan orb spinning on its side. Indeed, Uranus's axial tilt is about 98 degrees, meaning it essentially rolls around the sun like a ball. When you arrive at Uranus, you find a world that at first seems subdued. Its turquoise atmosphere is almost featureless to the casual glance, just a slight shading from turquoise to deeper teal toward the poles. But careful inspection reveals faint banding and occasional white cloud streaks, likely methane ice clouds high in the atmosphere. Uranus has a faint haze that gives it its uniform appearance. This sideways planet has peculiar seasons. Because it's tipped so extremely, each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness, since one Uranian year is 84 Earth years. Right now, say, it might be that the North Pole is in full sunlight, a bright cap, while the South Pole is in a long dark winter. This tilt might be due to a cataclysmic collision in Uranus's early history that knocked it over. The consequence is extreme but weirdly static seasons. At solstice, one hemisphere bakes, while the other freezes in darkness. However, bake is a relative term here. Even the sunlit pole's atmosphere is frigid, around 200 degrees C, and strangely, Uranus exhibits very little internal heat flow. Unlike its neighbor Neptune or the gas giants, Uranus's interior does not emanate significant extra heat, leaving its atmosphere relatively calm and cold. As you get closer, you notice Uranus is encircled by a set of thin, dark rings. They are much narrower and darker than Saturn's, composed of dark reddish material, likely tholins or radiation-darkened organics on ice. There are about 13 known rings, all quite faint, discovered in 1977 when they occulted a star. They appear as narrow charcoal black hoops around the planet's equator, which is tipped 90 degrees from its orbital plane. So the rings are often seen nearly face-on from the Sun's perspective, alternately showing us their broad face or edge depending on Uranus's position in its orbit. You also spot at least a few small moons embedded among those rings, shepherd moons that keep the ring particles corralled. Uranus has a retinue of at least 27 moons known. The larger ones are intriguing icy worlds themselves: Titania, Oberon, Ariel, Umbriel, and Miranda. Let's briefly visit one or two. Miranda is the smallest of the major moons, but perhaps the strangest. Its surface looks cobbled together from mismatched pieces. Part of it is old, heavily cratered terrain, but then there are bizarre regions that look like no other place, with huge fault canyons up to 20 kilometers deep, chevron patterns of ridges and troughs, and areas that seem almost like they were shattered and reassembled randomly. It's as if Miranda was broken apart by an ancient impact and weakly reformed into a jumbled mosaic. The gravity on Miranda is so low, less than 1% of Earth's, that you could easily hop off a tall cliff and not fear a lethal fall. You would drift down gently. In fact, off Miranda's cliffs, one of which, Verona Rupes, is touted as the tallest known cliff in the solar system, about 20 kilometers high, an object could take many minutes to drop to the bottom. Ariel and Umbriel are mid-sized moons, one bright and one dark. Ariel shows many signs of past geologic activity, a network of valleys and smooth plains that suggest internal ice melted and repaved parts of the surface in the past. Umbriel is darker, an old and shadowed world with many craters and a mysterious bright ring on one crater floor like a frosty deposit. Titania, the largest, shows long canyons and faults too, hinting it was once somewhat active. All these Uranian moons orbit in the planet's equatorial plane, which means they too are flipped on their side relative to the Sun. So at solstice,
One hemisphere of each moon is in continuous sunlight, and the other in darkness for years, just like Uranus itself. One can imagine bizarre effects of such prolonged day-night cycles on any potential volatile ices, maybe subtle migration of surface frost from the hot pole to the cold one. The environment out here is hushed and dim. Uranus's magnetosphere rotates on its side, resulting in complex interactions with the solar wind. As you depart the Uranian system, you note the aquamarine planet receding, encircled by its thin black rings and tiny spark moons, a silent, tipped-over world doing its slow roll around the sun. Pressing farther out, you reach Neptune, the outermost known major planet. Neptune is the twin of Uranus in size and composition. Both are ice giants, with a mix of hydrogen, helium, and a higher proportion of water, ammonia, and methane ices in their interiors. But Neptune has a much more dynamic personality. As you approach Neptune, you see a rich azure blue planet with a few obvious features. There is a dark oval storm system reminiscent of Jupiter's red spot, the Great Dark Spot, though by now it might have dissipated since it was last seen by Voyager 2 in 1989. Neptune's dark spots come and go. You also see high-altitude bright white clouds, likely methane ice cirrus, casting shadows on layers below as they race around in Neptune's fierce winds. Indeed, Neptune holds the record for the fastest atmospheric winds in the solar system, with jet streams up to 2,000 km/h. How such ferocious winds arise on a planet receiving so little solar energy is still somewhat mysterious, but Neptune does radiate more internal heat than Uranus, fueling more weather. At Neptune's south pole, the one Voyager saw sunlit, a haze of orange smog was observed, perhaps some warming effect creating slight color change. Neptune too is tilted, about 28 degrees, similar to Earth's 23 degrees. So it has seasons, though each season lasts over 40 years given its 165-year orbit. Currently, perhaps the southern hemisphere is transitioning to darkness and the north coming into light. Observations from Earth's telescopes in recent years have shown that Neptune's clouds and storm activity wax and wane with seasons. For instance, more frequent dark spots and bright clouds at certain times. Like all gas ice giants, Neptune has rings as well. Neptune's rings are faint and reddish, and not uniform. Intriguingly, they have clumpy segments called ring arcs, particularly in the outermost Adam's ring. These arcs, named Liberté, Égalité, Fraternité, and Courage, puzzled astronomers because orbital mechanics say a continuous ring should spread out evenly, yet here, material clumps in certain sections. It's now thought that one of Neptune's moons, Galatea, herds these arcs gravitationally and keeps them from dispersing. Neptune has a retinue of moons, 14 known. The standout is Triton, one of the most fascinating moons in the solar system. When you arrive at Triton, Neptune's largest moon, you are met with an icy pinkish landscape. Triton orbits Neptune in a direction opposite to Neptune's rotation, a retrograde orbit, strongly suggesting it was a captured Kyper belt object rather than forming alongside Neptune. Because of this, Neptune's gravity is gradually pulling Triton inward. In some distant future, billions of years, Triton will either break apart into a ring or crash into Neptune. But not yet. Triton's surface is extremely cold, about 235 degrees Celsius. Cold enough that nitrogen exists as frost and methane, and carbon monoxide ices decorate the surface. Voyager 2's flyby revealed Triton's surface to be surprisingly complex and young in places. Large swaths of terrain with few craters, indicative of recent reshaping. At Triton's south polar region, a cap of faint pinkish nitrogen ice and methane ice lay with dark streaks across it. Those streaks, it turned out, were the fallout from geysers. Yes, Triton too has active geysers. When sunlight in the southern spring warmed transparent layers of frozen nitrogen, it likely caused sublimation and pressure build-up beneath, eventually erupting
as geysers of nitrogen gas, carrying dark dust up to 8 kilometers high. The gas then blew downwind, depositing the dust in dark plumes that extended many tens of kilometers. You might witness one of these right now. Imagine standing on Triton's endless plain, dubbed the cantaloupe terrain, because its texture looks like a cantaloupe rind, likely due to diapirs or rising blobs of ice causing the surface to deform. In the distance, a whisper-quiet geyser begins. An invisible jet of nitrogen gas lofts, a column of fine, dark particles. Because Triton's atmosphere is extremely tenuous, only a fraction of a pascal of pressure, you cannot hear anything, but you see a faint, hazy plume rising and drifting sideways ever so slowly. The sky is a pale peach near the horizon from the thin haze, and above it quickly darkens to black. The sun is weak, barely providing any heat. You can feel the deep cold even in your insulated suit. Triton's terrain has variety. The cantaloupe region, the polar caps, and weird zones of what look like melted terrain, possible cryovolcanic landscapes where slush may have erupted in the past and refrozen into smooth plains. You move over a region called Leviathan Patera, an irregular walled depression that could be a collapsed caldera of an ice volcano. Near the terminator line, where day meets night, you notice the glint of starlight on what appears to be smooth, reflective surfaces. Could these be lakes of liquid nitrogen? Possibly not stable, but maybe transient pools when seasonal heating allows some melting of the nitrogen ice. Neptune's other moons are far smaller. Nereid, Proteus, a large, irregular dark chunk, heavily cratered, that Voyager imaged, nearly filling its Roche limit around Neptune but stable, and several newly discovered tiny ones. But none approach the interest of Triton. Now you have traversed all 8 major planets from the bright furnace of the Sun's vicinity to the twilight realm of Neptune. Beyond Neptune, the formal boundary of the classical solar system, there lies the vast expanse of the Kyper belt. Once, Pluto was considered the 9th planet, but we now know it as one of the largest members of this belt of icy bodies at the fringe of the Sun's influence. Your journey continues outward, and soon you encounter Pluto, shimmering dimly with a faint beige-white color mottled with darker patches. Pluto is a small world, only about 2/3 the size of our moon, but it is rich in character. As you draw near, you see an enormous bright heart-shaped feature dominating one hemisphere. This heart is Tombor Regio, and its western lobe is a vast basin of nitrogen ice called Sputnik Planitia. This frozen plain is unlike anything you've seen. It's a smooth, cream-colored expanse with subtle cellular patterns on it. Those cells are outlines of convection within the nitrogen ice. Yes, the frozen nitrogen here, soft as wax, is slowly churning over eons, like a gigantic lava lamp of frost. This convection constantly renews the surface, erasing craters, so Sputnik Planitia is essentially craterless and very young in appearance. You skim low over it and realize you're flying above a frozen sea of molecular nitrogen. In places, you see pits where nitrogen has sublimed away. In others, where perhaps a recent impact delivered a jolt of heat, the nitrogen might have melted and refrozen. At the edges of the heart-shaped plain, you find towering water ice mountains named Hillary Montes and Norgay Montes. Some peaks reaching 4 to 5 kilometers high, thrusting jaggedly above the plains. Water ice on Pluto is as strong as rock and forms the bedrock that the softer ices, nitrogen, methane, carbon monoxide, overlay. These mountains may be uplifted blocks of water ice or the rims of an ancient impact basin, now filled by Sputnik's ice. North of the heart lies a rugged highland of older ice, cut by canyons and dotted with crater depressions. To the east, a vast region of reddish-brown hues called Tartarus Dorsa is covered in strange aligned ridges like scales or bark. They call them bladed terrain, likely huge sublimation sculpted cliffs of methane ice. Perhaps where volatile ices have preferentially vanished, leaving behind the harder stuff in blade-like formations oriented by sun exposure and wind. On the dark anti-heart side of Pluto lies a large, diffuse, dark region called Cthulhu Macula, a possibly organic-rich expanse, older and heavily cratered in spots, with a draping of dark tholin, complex organic molecules created by UV light acting on methane, giving it a ruddy charcoal color. Sunset on Pluto comes swiftly. The sun is just a brilliant star here, providing twilight-level illumination even at noon. As darkness falls, the sky reveals something wondrous, a soft blue haze around Pluto, surprising for such a small world. This haze is made of layered photochemical smog. Sunlight, even weak, triggers chemical reactions in the thin atmosphere, converting methane into complex hydrocarbons, which then condense into tiny particles, creating a delicate multi-layered haze up to 200 kilometers high. The haze is visible when the sun is low, scattering blue light, giving Pluto's limb a cerulean halo. Through that haze, you might see the pinprick of the sun setting and also another pinpoint shining. That would be Charon, Pluto's largest moon. Charon is half the diameter of Pluto, so big compared to Pluto that the two orbit each other around a point in space between them. One could call Pluto-Charon a double dwarf planet system. They are tidally locked to each other, always showing the same face to one another as they twirl in a 6.4-day dance. You decide to pay Charon a visit, drifting across the 20,000-kilometer gap separating them. Charon is grayish, with a dark reddish polar cap. A cap that likely comes from gases escaping Pluto and getting trapped and frozen onto Charon's pole during winter, where radiation then chemically alters them into red tholins. Charon's surface shows an expansive system of chasms, a giant belt of fractures that wraps around, indicating that at some point, Charon's interior water may have frozen and expanded, cracking the crust. There is a prominent large crater with bright rays near the equator, called Arakoth, impact by some, though unofficial, which hints that beneath any weathering, Charon's water ice is relatively clean and bright when excavated. On the far side of Charon, which we did not see via spacecraft, presumably more craters dominate. Charon has no atmosphere to speak of, so its surface is static and dead-looking, but still fascinating as a record of what goes on at the solar system's edge. Looking back at Pluto from Charon, you see Pluto's hazy silhouette occulting the distant sun, and a ring of light around Pluto's limb, an atmosphere and haze backlit, glowing a faint gold and blue. This reminds you that even these tiny worlds have complexity and beauty. Pluto's atmosphere is extremely thin, about 100,000 times thinner than Earth's at surface. Mainly nitrogen with some methane, but it is escaping gradually as Pluto can't hold it forever. In Pluto's sky during day, that atmosphere would likely produce a blue tint, and one could even see a faint sunbeam or twilight after sunset due to the haze. Departing Pluto and Charon, you now sail truly into the unknown dark. The sun becomes just one star among many, albeit the brightest. You have entered the Kyper belt fully. Here exists a vast collection of icy bodies, leftover planetesimals from the solar system's formation, preserved in cold storage. Many of these are small, irregular chunks, only a few kilometers wide, but some are quite large, Pluto's size and bigger. In fact, not far beyond Pluto in a cosmic sense lies Eris, a dwarf planet slightly smaller than Pluto, but more massive, with an even higher density, suggesting less ice fraction. Eris is so far from the Sun that its atmosphere, if it has one, is entirely frozen onto its surface most of the time. When nearer perihelion, perhaps a thin layer of atmosphere sublimates. Now at aphelion, likely it's frozen solid. Eris's surface is extremely reflective, perhaps from a coating of nitrogen or methane ice, making it one of the brightest objects in the Kuiper belt. There are also Haumea, an elongated, rapidly spinning dwarf planet with a weird shape and a family of collisional fragments trailing it. Makemake, another bright reddish dwarf planet slightly smaller than Pluto, and numerous others being discovered each year. The Kyper belt extends from about 30 AU, Neptune's orbit, out to roughly 50 AU in a broad torus around the Sun's ecliptic plane. The population here moves in leisurely orbits around the Sun, taking hundreds of years to complete one circuit. Occasionally, gravitational nudges, perhaps from Neptune's past migration outward, have scattered some objects into eccentric or inclined orbits. Some cross Neptune's path, like Pluto, a resonant KBO locked in 3-2 resonance with Neptune. Others have been flung into even more distant orbits. As you continue outward, you pass countless unseen worlds. One such world presents itself in your path, a contact binary shaped like two lumpy spheres stuck together, resembling a snowman. This is similar to Arakoth, which New Horizons visited in 2019, likely a primordial object that formed by the gentle merger of two separate bodies. Its surface is very red from organic compounds, and it has no craters or geologic activity. It's a frozen time capsule from the birth of the planets. Such objects abound out here. Now the Kyper belt's outer edge appears. The density of large bodies thins out beyond about 50 AU. You are entering now the deep freeze, the realm of the comets. Out here, the sun is but one of billions of stars in the sky, and the warmth and light are feeble. This is the beginning of the Oort cloud, though at first perhaps better to say the scattered disk, a transitional region with objects on very elliptical or inclined orbits, which sometimes bring them far out, hundreds of AU, before returning toward the sun. You might pass one such traveler, perhaps a comet nucleus quietly drifting at aphelion, building up a dark crust of complex organics as cosmic rays process its ices over eons. At this distance, it is just an inert black potato a few kilometers across, waiting until one day a stellar perturbation or gravitational resonance nudges it onto a trajectory inward, where it will sprout a glowing coma and tail and be reborn as a comet, blazing in the inner solar system's skies. But beyond even these distant scattered objects lies the true boundary of the Sun's kingdom, the Oort cloud. It is not a flat belt, but a vast spherical swarm of countless icy bodies surrounding the solar system in all directions. A shell of potential comets extending perhaps as far as 100,000 AU, nearly 1.5 light-years, from the Sun. This region is mostly empty space, with objects tens of millions of kilometers apart, but within it reside perhaps trillions of comets. These are ancient leftovers from the formation of the outer planets that were flung out here by gravitational interactions long ago, or they are outer solar nebula condensations that never coalesced into larger bodies. Here, the Sun's gravity is so weak that passing stars, or even tides from the Milky Way's mass distribution, can perturb or dislodge these comets. You find yourself floating in the darkness between stars. The Sun is a very bright star behind you, but no longer overwhelmingly so. You can even look straight at it without shielding now, as it's barely brighter than Venus as seen from Earth, just a point of intense light. Out here, in the silence and darkness between the stars, as a NASA text once described the Oort cloud, you have reached the threshold of interstellar space. The icy nuclei of comets drift like sleepy moths around a porchlight, as one poetically put it, the porchlight being the distant sun, now just one star among many. Pick one such Oort cloud object, say, an untouched comet nucleus named perhaps after some catalogue number. It is an irregular body a kilometer or two wide, surface pitch black with some reflectivity, maybe only a few percent. It might have a crust of tar-like organics covering a matrix of ice and dust inside. It has been in deep freeze for 4.5 billion years, nearly unchanged since the time it formed close to the Sun, before being ejected to the fringe. Occasionally, over the millennia, a passing star's gentle tug perturbs its orbit slightly. Most times, it remains bound to the Sun, but sometimes, rarely, such nudges send an Oort cloud body falling inward as a long-period comet. Perhaps one day, this particular one will do so and delight future skywatchers with a bright tail. At the moment, however, here at roughly 30,000 AU from the Sun, you are effectively beyond the heliosphere. In fact, you likely pass the heliopause, where the solar wind's influence yields to the pressure of the interstellar medium, back around 120 AU, a tiny fraction of the distance to the Oort cloud's far edge. That boundary is where Voyager 1 and 2 transitioned into true interstellar space in recent years. Now you are well beyond that, immersed in the sparse interstellar gas of our galaxy. Charged particles from the Sun no longer dominate. Instead, cosmic rays, high-energy particles from distant stellar events, roam freely. Magnetic fields from the galaxy thread through space, only slightly perturbed by the Sun's faraway presence. As you drift still outward, even the Oort cloud becomes tenuous. Eventually, at around perhaps 100,000 to 200,000 AU, about 2 to 3 light-years, the Sun's gravitational grip on comets is at its limits. You are now truly in between the stars. It is dark. Dark beyond any night you experience near Earth, because here no nearby sun lights any sky. Yet, it is not pitch black. Look around. The Milky Way galaxy is a glorious band across the sky, far richer and brighter than from Earth because there is no atmosphere or light pollution. You see the combined glow of billions of distant stars in that band. You also see many individual stars too, brilliant blue-white ones, closer yellow ones, distant red ones. One of those stars, shining with a steady golden light behind you, is the Sun as seen from here. Surrounding it, if you squint, you might just detect a very faint spherical cloud of comets reflecting its light weakly. The Sun's aura of Oort cloud. Take a moment in this deep space to consider scale. It took light about a year to travel from the Sun to your current position. The nearest star to the Sun, Proxima Centauri, is still about 3 light-years further on. The emptiness is profound, but not absolute. There are wisps of interstellar gas and dust. You might encounter a diffuse molecular cloud, a region with slightly higher density of hydrogen molecules and dust, perhaps the birthplace of future stars. Out here, as you cross into the domain of the galaxy, you can almost feel the transition. Your spacecraft's instruments detect a change in the charged particle population. Galactic cosmic rays are the main contributor now. You are now in the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars and makes up much of the volume of the galaxy. If your eyes could see in radio or other wavelengths, you might notice the subtle glow of the cosmic microwave background in all directions, or emissions from distant nebula. But visually, it's the stars and the dark that command attention. Now your perspective begins to widen. With the Sun now just another star behind you, you turn your gaze to the Milky Way as a whole. Imagine rising above the plane of the galaxy, which requires magical rapid travel on your part, beyond realistic speeds. But in this thought journey, you can transcend such limits at will. As you gain a bird's-eye view of our galaxy, its structure emerges. A majestic spiral disk with arcing arms of starlight and dark ribbons of dust. The Sun resides in a minor spur between major arms, about 27,000 light-years from the galactic center. From above, you locate the Sun's position, not marked by anything obvious, just one G-type star among billions, currently in a small local arm segment called the Orion Arm or Orion Spur that connects the Sagittarius and Perseus arms. If you mark it mentally, you can trace the Sun's slow orbit around the galactic center, one circuit every 230 million years or so. The galaxy's disk is a flat glowing storm of stars, gas, and dust, roughly 100,000 light-years across. The central region is a swollen bulge of older yellowish stars, within which lies the very hub, a mysterious bright radio source known as Sagittarius A, which is the location of a supermassive black hole around 4 million times the mass of our Sun.
You cannot see the black hole directly, unless you have radio or X-ray eyes, but you see the effects. Stars orbiting a seemingly empty point at incredible speeds, and sometimes flares of high-energy radiation as material gets accelerated and swallowed. The center is ringed by a torus of gas and possibly peppered with X-ray binaries and exotic objects near the black hole. If you were to venture there, you would find space severely curved by gravity and the density of stars unbelievably high, a chaotic, energetic environment. Radiating outward from the central bulge are the spiral arms. These arms are not physical arms, like solid appendages, but rather regions of higher density that propagate through the disk, triggering star formation in their wake. As you look at the Milky Way's face, you identify the major arms. The Perseus arm is prominent, sweeping along the outer part of the galaxy. The Scutum Centaurus arm, which passes nearer the center and out. Perhaps two main symmetric arms in a grand design spiral pattern, and some spurs and feathering branches aside, like the Orion spur where the sun is. In the arms, you see blue patches and pink knots. These are hot young stars and glowing nebulae respectively. Giant molecular clouds in the arms collapse to form new stars, and those newborns, massive hot O and B stars, illuminate the surrounding clouds, H2 regions glowing pink with ionized hydrogen, and shape them with stellar winds. The blue star clusters shine strongly, but briefly before their stars die in supernovae. Indeed, scattered throughout the arms, you also see the remnants of past stellar death, supernova remnants, expanding shells of gas like the Crab Nebula or Vela, emitting tendrils of enriched material back into the interstellar medium. These events seeded heavier elements, carbon, iron, etc., into the galaxy, the very elements that later incorporated into new stars and planets, and into you and me. Between the arms and swirling around, an ethereal mist of diffuse interstellar gas persists. Dark patches in the galactic disk silhouette against the starry backdrop. These are enormous dust clouds blocking visible light. One famous such dust lane splits the Milky Way as seen from Earth, the Great Rift, caused by clouds in the inner arms. But from above, you just see them as dark swathes in the disk. If you had infrared vision, however, the dust becomes more transparent and you see even more myriad stars hidden behind. The whole galaxy rotates. The stars in the disk orbit the center in roughly the same direction. But intriguingly, the rotation curve, how orbital velocity changes with distance, is flat. Stars far out orbit just as fast as those closer in, defying the expectation if only visible matter existed. This was one key clue for the existence of dark matter, an unseen mass component enveloping galaxies. So though you do not see it, you know that the Milky Way is embedded in a vast halo of dark matter, extending well beyond the visible disk and containing perhaps 5 times more mass than all the stars and gas combined. This dark matter neither emits nor absorbs light. It interacts only gravitationally, and perhaps through some other weak forces yet unknown, but it provides the gravitational scaffold that holds the galaxy together and the cosmic web beyond. Beyond the disk and bulge, you find the stellar halo, a sparse spherical distribution of ancient stars and globular clusters. Globular clusters, as you see, are compact spheres of tens of thousands of very old stars orbiting the galaxy in all directions. They appear as glittering dense balls, mostly toward the galactic bulge, but also some far out. These are fossils of the early galaxy formation, essentially. The halo stars and clusters often have very low heavy element content, metallicity, indicating they formed before previous generations of stars had seeded the environment with heavy elements. There are about 150 known globular clusters swarming around the Milky Way, each like a beehive of stars, perhaps 12 to 13 billion years old.
Their orbits take them plunging through the disk and out again, oriented randomly. Our vantage now drifts further outward, and the whole Milky Way appears smaller. You note it is a barred spiral galaxy. The central bulge has a bar structure, a stretched nucleus of stars, from whose ends the spiral arms likely emanate. Indeed, surveys of stars at the center show an elongated bar shape. Such bars are common in spiral galaxies and can drive gas inward, perhaps helping fuel star formation or feed the central black hole. The Milky Way's bar is subtle to our eyes, but distinct in infrared studies. Encircling the Milky Way is also a tenuous halo of hot gas, observed via X-ray emission, and even the remnants of past devoured galaxies, streams of stars that were torn from dwarf galaxies that ventured too close, now wrapping around the galaxy in giant loops. Now your mind's eye travels even further out, such that the entire Milky Way is seen as a small spiral among others. The night sky as we know it with constellations is but one perspective from within. From out here, those constellation patterns disappear as you see the true 3D arrangement of stars. The Milky Way appears about 100,000 light-years in diameter, with the disk perhaps only 1,000 light-years thick. It contains perhaps 200 to 400 billion stars, hard to count precisely, plus interstellar gas equal to maybe 10 to 15% of the total luminous mass, and that central black hole. Now you begin to perceive that the Milky Way is not alone. It is part of a small cluster of galaxies we call the local group. The nearest big companion is the Andromeda galaxy, M31, a spiral slightly larger than the Milky Way, about 2.5 million light-years away. You turn your view toward it, a grand spiral with perhaps 1 trillion stars. Even from Earth, it's visible as a smudge in dark skies. From this omniscient vantage, you see its spiral arms and dust lanes clearly. It too has satellite galaxies. In fact, as you look between the Milky Way and Andromeda, you notice many small elliptical fuzzballs and irregular fragments. These are dwarf galaxies bound in the local group. The Milky Way alone has dozens of known dwarf satellites. The large and small Magellanic Clouds are the most luminous, visible as cloudy patches in the southern Earth sky, but also fainter ones like Sagittarius Dwarf, currently being tidally disrupted, Draco, Ursa Minor, Sculptor, Fornax dwarfs, and many ultra-faint dwarfs discovered in recent surveys. Andromeda has its own entourage of dwarfs. The third largest member of the local group is the Triangulum galaxy, M33, a graceful smaller spiral orbiting perhaps around Andromeda. As gravity dictates, Andromeda and the Milky Way are actually moving toward each other. In about 4 billion years, they will begin to collide and merge, dancing a gravitational waltz that will fling stars into new orbits and trigger cascades of starbirth as gas clouds slam together. Eventually, they will likely form a single elliptical galaxy, sometimes nicknamed Milkomeda. But for now, they are distinct island universes, drifting closer in the cosmic ocean. Our local group is falling toward a larger structure, the Virgo cluster, a massive cluster of galaxies about 50 to 60 million light-years away, containing thousands of galaxies. Indeed, step back further, and you behold that galaxies collect into clusters and superclusters along filaments, with great voids in between, the cosmic web. The local group and the Virgo cluster, and others, are part of the Virgo supercluster, or local supercluster, although modern understanding defines an even larger entity called Laniakea supercluster, which includes Virgo and other clusters, all gravitationally moving together. At this truly grand scale, a few 100 million light-years across, the pattern of the universe emerges clearly, like a sponge or foam, where galaxies are concentrated along filaments and sheets surrounding vast, empty voids. It's as though the large-scale structure has a web-like or honeycomb pattern. This is the cosmic web, the result of initial tiny density fluctuations in the early universe that grew under gravity into the complex structure of clusters and voids. The nodes of the web are rich clusters of galaxies, like Virgo, connected by filaments, lines of galaxies and groups, and between them lie voids 100 million light-years across with very few galaxies. One might wonder, why this filamentary structure? Cosmological simulations and observations tell us it's due largely to dark matter scaffolding. Dark matter clumped first, forming a web-like structure under gravity, with voids where there was slightly less matter initially. Normal matter fell into those gravitational wells, forming gas clouds that became galaxies at the nodes and along filaments. Over billions of years, gravity steadily draws matter into this web, making clusters grow by accreting smaller groups and the filaments draining into clusters. Our local group is on an outskirt of the Virgo cluster, likely slowly being pulled toward it. At these scales, you also become aware of the mysterious presence of dark energy, an even more enigmatic component of the universe. About 70% of the total energy content of the universe appears to be in this form. It does not cluster like matter. It is uniform, permeating all of space, causing space itself to expand at an accelerating rate. Whereas gravity, from matter, works to slow expansion and pull things together, dark energy pushes space to expand faster. About 6 billion years ago, dark energy's effect became dominant over matter's self-gravity, and since then the expansion of the universe has been speeding up. Thus, while a localized cluster like Virgo can overcome expansion due to its own gravity binding it, distant clusters are receding from each other at ever-increasing speeds.
Now, imagine time as well. You look far enough out in space. You also look back in time, because light takes time to reach you. So at the largest scales, you can see glimpses of the early universe. For example, the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, comes from all directions. From a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and became transparent. It's a faint glow primarily in microwaves now, due to the redshift from the expansion, but it shows tiny temperature fluctuations, the seeds of the future galaxies and clusters. That is the ultimate horizon of the observable universe for electromagnetic waves. Beyond that, the universe was opaque plasma, but neutrinos or gravitational waves can give hints from even earlier. Your journey of the mind now spans 13.8 billion years of history and tens of billions of light years of space. You witness how from a nearly uniform hot plasma, the cosmos expanded and cooled, forming hydrogen and helium gas, which coalesced into the first stars and galaxies a few 100 million years later. Those first stars, population 3 stars, were massive and short-lived, exploding as supernovae that enriched the cosmos with heavier elements. Galaxies formed and merged and grew. In the centers of many, massive black holes formed early and grew by accreting matter, sometimes shining as quasars that outshone entire galaxies with their brilliance. You could see in extremely distant galaxies, thus, early in time, these quasars and proto-galaxies flickering in the cosmic dawn. Over billions of years, galaxies matured into the shapes we see today. Some became ellipticals, often from mergers of spirals. Others remained spirals. Dwarf galaxies aplenty swarmed around bigger ones or drifted lonely in voids. Clusters assembled. Bubble-like voids grew as matter flowed into structures. Now consider that all the while, through the vastness of space and time, the atoms that now make up your body were forged in this cosmic process. The hydrogen in your cells likely formed minutes after the Big Bang. The carbon, oxygen, nitrogen in your body were synthesized in the core of a star that lived and died before our sun was born. The iron in your blood, the calcium in your bones, those came from the violent explosion of a supernova scattering its enriched guts into space. That dust and gas then coalesced 4.6 billion years ago in a swirling disk around the young sun to form Earth and all life's ingredients. The water you drink likely contains hydrogen from the beginning of time and oxygen from long-dead stars, combined on Earth perhaps by chemical processes involving those same elements. Eventually, perhaps inevitably, from this mix of elements on Earth, life emerged, and eventually that life evolved to conscious beings able to ponder their origins. We are such stuff as the stars made, literally stardust brought to life. The space out there is not just black void. It is the matrix from which everything came. From this grand perspective, slowly you make your way back home. Zooming in from intergalactic space, you find the local group, the Milky Way, one of its spiral arms, the Sun, and our pale blue Earth circling it. You see Earth anew, a bright blue oasis amid the darkness, its white clouds swirling in an active dance, its polar caps gleaming, its green-brown continents showing hints of forests and deserts. Sliding down through Earth's comforting atmosphere, you return to where you began, sunlight warming human skin, wind rustling through leaves. Perhaps it's sunrise now. The sun peeks over the horizon, lighting dewdrops on grass into tiny rainbow sparkles. You feel the gentle warmth again on your face. Only now you carry the awareness that this warmth has an ancient, epic journey. From the core of our star where it was born, across the vacuum of space, touching worlds on the way, reflecting off moon and rings, until finally it caressed your cheek. You open your eyes. Above, the morning sky is blue and quiet. The same sun whose fires we skimmed now lights up the clouds in shades of pink and gold. The same earth where life flourishes now lies beneath your feet, solid and nurturing. You realize something profound. The line between us and space is an illusion of perspective. The air you breathe was assembled from atoms gathered across the galaxy. The heat in your body is the stored energy of the sun's rays, captured by plants and passed as food to you. The calcium in your bones was forged in a star's supernova ash. The very concepts of today and yesterday make no sense without the cosmic cycles of Earth's rotation and orbit. You are not separate from the universe. You are a part of its exquisite ongoing story. In this moment of stillness, standing on Earth under the sun's glow, you can feel the unity of it all. The solidity of the ground, the cool whisper of the breeze, the distant glitter of stars that will appear by evening. It's all connected. The space that seems so remote is in fact within you, around you, of you. When you gaze at the night sky, you are looking into your own cosmic past. When you feel the sun's warmth, you are touching a nuclear furnace 150 million kilometers away that gives life to our world. When you drink water, you consume molecules that likely migrated through cometary ice and Earth's primordial oceans over eons. Returning to that gentle, contemplative breath you began with, you understand now that space is not a distant void separate from human existence. It flows through everything. The atoms in your body were scattered across space before coming together here and now. The gravity of the Earth that holds you is the same force that shapes the orbits of planets and the dance of galaxies. The light that lets you see has traveled years or minutes or seconds through space to reach your eyes. As the day progresses, you carry this awareness with calm wonder. Our planet Earth, with all its busy life, is embedded in the vast cosmos like a small bright fleck in a great ocean. But we are not adrift or isolated. We are profoundly connected to that ocean. We are made of it. The boundary of atmosphere and space is no boundary at all, merely a gradual thinning of the air. Space is already here. It begins a few dozen kilometers above us and extends outward indefinitely. Earth floats in it.
And space even permeates the atoms within us, mostly empty space inside atoms too. The journey outward and back has etched into you a quiet understanding. The universe is not a separate place you visit. It is home. From the sun's warm light on your skin, to the elements in your blood, from the moon's pull on the tides, to the spark of thought in your brain, powered by chemical energy that ultimately traces back to the sun, you are a miniature universe within the universe, a conscious fragment of the cosmos contemplating itself.
Above, the sky has turned a deep daytime blue. Somewhere beyond that blue, planets are orbiting, stars are burning, the galaxy is rotating, and the universe is expanding, all in majestic silence and scale. But here, right now, you feel no disconnect from those faraway happenings. They led inexorably to this moment. And in every moment going forward, the atoms that compose you will someday return to the Earth, perhaps become part of new life, and eventually return to space when Earth itself is engulfed by the sun's red giant phase long in the future. Even that is not an end, but a transformation. Maybe some of our atoms will float in a planetary nebula, or be part of the sun's remnant white dwarf, or get incorporated into a new star system.
Space is not cold nothingness. It is the cradle of everything that is. It is the gentle night that holds all our days. It is the canvas on which the galaxies paint their histories, and on which each of our lives is drawn as well. Feeling this unity, you stand quietly as the sun climbs a bit higher, spreading golden light over the waking world. In the morning air, you inhale deeply. The breath fills your lungs, and you realize it contains argon atoms exhaled by dinosaurs perhaps, and before them by amphibians crawling out of ancient seas, and before them by bacteria in primordial mats, and now by you. Eventually, those argon atoms, chemically inert, will still be part of Earth's atmosphere when the sun leaves the main sequence. A soft smile forms. You see that nothing is ever truly lost in the universe. It only changes form. The energy that was in the core of a star now powers the beating of your heart. The soul, if you will, of every person is built of the soul of the cosmos. From the sun's serene rising to the stars that will sprinkle the dusk, from the ground underfoot to the faint nebulae in telescopes, it is all one continuous story, one breath, one orbit, one unfolding miracle. The space that surrounds us is also within us. We are the universe, and the universe is us. Space is not separate from us, it is us.